made on these territories. We acknowledge the harms and mistakes of the past, and we dedicate ourselves to move forward in partnership with Indigenous communities in a spirit of reconciliation and collaboration. So with that, we'll get started. I'd like to introduce our first speaker tonight. It's our very own Scott Young, and Scott will be talking all about getting ready for galaxy season. Please welcome Scott Young.
Thanks, Liz. We'll just flip a couple of things over here. I hope for the folks that are online, you can hear what's going on, because that's part of the point. Let's just get to the other presentation here. And go back to sharing screen. Okay, so we say getting ready for galaxy season in the spring. It turns out that it's always galaxy season because galaxies are the most common deep sky object out there. But we're really looking at, why are we showing that one? Sorry, make sure we share the right screen here. There we go. So we're really talking about bright galaxies because there are galaxies everywhere. And the only proper way to start a galaxy talk is, of course, with the wonderful Star Trek or Star Wars opening a long time ago in a galaxy far, far away. So imagine a long time ago in a galaxy far, far away, a photon of light is emitted from some star, and it is emitted out into the universe. And it manages to make it all the way through its own galaxy, the spiral arms, the dust clouds, the dark matter, all of the other stars and things like that. And it leaves its own galaxy and it heads out into intergalactic space. And then it keeps going at warp 1. There's my Star Trek reference. The speed of light, 300,000 kilometers per second, more or less. And it keeps going out into intergalactic space for millions of years, immense amounts of time. And it eventually encounters another galaxy, and it gets into that galaxy and it manages to avoid all the nebulae and the dark clouds and stars and things like that. And it heads towards a little star in the outer rim of the galaxy. And in the last fraction of a billionth of a second before anybody sees that photon, it gets absorbed by a cloud 10,000 meters above the surface or whatever. You wind up with a horrible journey. If we have a clear sky, though, that piece of light, that photon from another galaxy that originated in a star millions of light years away can get inside your head, go in through your eye and interact with your body. Like, we're talking about energy transference across galaxies. You know, Carl Sagan used to always say things like, we're made of stardust, all of the atoms in our body are forged in stars across the Milky Way. Yeah, that's cool. But with your telescope, you can see light from way farther away that makes that connection with the cosmic very clear as well. So that's why I like observing galaxies, and that's why I like to gear up for springtime. Well, why is spring the bright galaxy season? Well, we're just coming out of winter. And in winter, when you're looking out into the sky, you're looking through the plane of the galaxy, our own Milky Way galaxy, which is big and round when you see it from the top, but it's really flat. It's like a pizza. And so in the wintertime, we're looking through the pizza out towards the outer edge. And so we see the Milky Way that is visible in Orion and sort of that area. And you've got nebula and star clouds and clusters and things like that. 6 months later or before, in the summertime, we're also looking through the plane of the Milky Way, but here we're looking in towards the center, the barred center of our spiral galaxy. And there's all those great dust clouds and dark nebulae and bright nebulae and things like that, that is down in the Scorpius and Sagittarius part of the galaxy. In between, we're looking out of our galaxy. And our galaxy is only, it's only this thick. So we only have this many stars to see. And then when we look out in the galaxy, beyond the galaxy, you are looking into that intergalactic space between galaxies. And there's nothing else to see until you see the other galaxies. So springtime and fall, that doesn't show up super great there. Let's just add the constellations. Springtime and fall, we're basically looking out of the galaxy in the sort of convenient evening times. And so do we have a laser pointer here? We don't. Can you see this pointer? Yes, you can. Yeah, okay. So the Big Dipper in the springtime is pretty much overhead. We've got Boötes over here with the bright star Arcturus. You've got Leo over here. You've got Virgo. And this is sort of this area here is basically looking out of the galaxy out into intergalactic space. You can still see the Milky Way sort of ringing the, oh, thank you, sir. You can still see the Milky Way sort of ringing the horizon, but we're looking away from all that out into this intergalactic space. And probably the most famous galaxy that people will look at is the Andromeda galaxy. This one's visible in binoculars, even to the unaided eye, but it's visible in the fall time. So we're not going to talk too much about it, but it is a great thing to look at. Most of the other galaxies in the springtime don't sort of stand on their own. They're in clusters, they're in groupings, they're in pairings and triplets and things like that. And we get an opportunity to see a whole bunch of galaxies sometimes at once. Here's the great Hubble field. You will not see this through your telescope. We'll talk about expectations in just a minute. So this is sort of the view of the spring sky looking towards the south. We've got Leo over here. We've got Virgo down over here. The Big Dipper is just off the top of the screen there, basically at the zenith. And the center of the chart is basically the realm of the galaxies. If you point your telescope in there and move around, you're going to see a lot of galaxies, but they're not super bright. But this is the area you want to hunt for. Now, this is the kind of map that Stellarium, the free software, presents for us. And I'd like to say that this is the kind of observing view that I have. I made my own custom horizon for Stellarium, and this is actually the view that I have from my house, with the giant tree and the neighbor's garage, basically blocking that entire area of the sky. I have about a 45-minute window where the Virgo cluster will come through the trees, so I have to time it just perfectly. But you do want to get to a nice observing site. So what do we have this here for? Sorry about that, folks. So to get ready for galaxies season, as we say, can I make this go away? Nope. You have to tune up three things. You have to tune up your telescope, tune up your technique, and tune up your expectations. And as I was putting this together, my oldest kid said, you have to make the third one start with a T, so it's the 3 T's. Well, we'll just do what NASA does and choose a different letter in the word for the acronym. So that it's the T of expectations there. So the 3 T's. Your telescope. You could see some of the brightest galaxies with binoculars, but the challenge there is to find them and to detect them. You're not going to see these amazing views. Oh, we're still not sharing? Okay. Where did it go? Yes, there we go. Okay. So you pretty much want a telescope to see galaxies. Now, luckily, the center has a whole bunch of them. We've got our loaner scopes, we've got the observatory and things like that. So if you remember, you probably have access to a decent telescope, even if you don't have your own. Make sure everything works. There's a lot of people put their stuff away for the winter, and there's no shame in that. My visual stuff stayed in the garage all winter, and that just means I have to dust it off and get rid of any detritus that the squirrels have left in the garage or whatever. So you have to make sure your optics are dust free. Anything that scatters light is going to make your galaxy expedition that much harder, because galaxies are very faint, and you want to make sure that your optics are sort of in their best situation. From a technique point of view, I do a lot of observing from my backyard, from my light polluted backyard in suburban Winnipeg, I can't see a lot of faint stuff. Any kind of external light is going to be a problem. So you don't want to go to a place that is very well lit. You want to get to a dark site if you can. You want to avoid the moon, of course. You want to avoid any sources of external light. That means don't look at your phone. The worst thing about the proliferation of the electronics in working your telescope is that you have to look at these bright monitors, which will kill your night vision. You really want to let your eyes dark adapt and keep them dark adapted. And then you can use your reverted vision to try and see these faint things, because the galaxies are going to be quite faint unless you have a really, really big telescope. And even then, you can push your optics farther if you can keep your eyes dark adapted. So that means when I go galaxy hunting, I print out my star charts and I take my little flashlight with the red nail polish over the bulb, and I use that for reading my paper charts. And then I can draw right on them, or I can make any notes or things like that. And the other thing that you should probably do is to have a plan. You need to know what you're going to look for, where it is, all that kind of stuff. This is applicable to most observing, but if you're just coming out of winter hibernation, it's a good reminder to sort of get your stuff together so that if you do drive out to a nice dark site, you don't realize that you get out there and you forgot the star charts on the printer, or you forgot your favorite eyepiece or things like that. I always throw night watch in the car because if everything else breaks down, night watch has a great set of star charts that will get me going and at least let me do some observing. Written by Terry Dickinson, who passed away just a month ago or so. Probably the best astronomy book written in Canada for a long time. And it does have a great set of charts of the galaxies, the galaxy region. So I recommend that as a backup. And then the Stellarium Star Program lets you print out custom maps, and you can even put your field of view and your finder scope and all sorts of things on it. And it really helps to find things in the sky. So you don't have to have really expensive tools, but you have to have some tools and know how to use them. Some of you were just outside talking about the Explore the Universe certificate. This is part of having a plan. You need to know what you're going to look for. The Explore the Universe certificate has 24 deep sky object options in it. Of those 24, only one is a galaxy. That should tell you a little bit about galaxies. They're not always the top of the list in terms of the best and brightest. But if you start looking at fainter lists, they become more populous. In the Messier list, out of 110 objects, 40 of them are galaxies. And of the NGC list, which is the New General Catalog, how many are in that? 7,800, something like that? 7,800 objects, more than 6,000 of those are galaxies. So as you get down into the fainter magnitudes, galaxies become the dominant object. With a big telescope, say a 14, 16, 18-inch telescope, you can point it into the Virgo cluster, and the challenge isn't finding the galaxies. The challenge is figuring out which one of the 12 galaxies you see is which. There are a lot of them out there once you get into large apertures and dark skies. But most of us are used to the Hubble images or the Webb telescope images or just astrophotographs that we see online. And we expect to see these glorious, colorful spiral arms and red nebulae and all sorts of things. That's not what we see visually. Our eyes function very, very differently. If you're a visual astronomer, you have to accept the fact that you will be basically looking at faint, fuzzy things. And a cynic would say that one faint, fuzzy thing looks a lot like another faint, fuzzy thing, especially if you don't pay too much attention. So the key is to pay attention. The key is to really interrogate what you're looking at, to look for a long time. Don't look at a galaxy for 5 seconds or 10 seconds. Look for 60 seconds without a break. And then maybe take a break or whatever, switch eyepieces and look again. Spend time with these objects. And that's when you start to see more and more of the details. And you can really push your vision because generally the inner part of the galaxy is very, very bright. The outer part is very difficult to see. And the more you look, the more you'll be able to see. So galaxies come in different flavors, different types, different shapes. Edwin Hubble came up with this sort of classification scheme. It's called the tuning fork diagram, and it basically is completely irrelevant astrophysically. It's completely irrelevant to anyone except someone who is looking at a galaxy visually with a telescope. Because it's not like the galaxies progress along here or are related in some way or anything like that. It's literally just a way of classifying what they look like. So you've got elliptical galaxies over here on the left, and like their name, they are basically roundish or ovalish. And the number after the E tells you how round they are. E0 ones are nice and round. E7 ones are very elongated, and all the different gradations in between. And then you've got spiral galaxies, which get broken into a couple of different classifications. There's the regular spirals up top here, where you've got a bright core and then spiral arms. And depending on how wide those spiral arms spread out, the galaxy is given another name, another letter, A, B, or C. And then in parallel to that, you've got the barred spirals, which are exactly the same thing, except instead of being having a circular central core, the central core is sort of elongated or stretched out, much like it is in our galaxy. And there you have, again, the A, the B, and the C. Any piece of software or any catalog will tell you what kind of galaxy a certain object is, and that can help you set your expectations, because most of the brightness of a galaxy is in the middle. And so if the galaxy is something like an E galaxy, where it's basically all round there, you can sort of figure out that you're going to see a bright round spot and then see how far you can see it before it fades out. If the galaxy is, say, an SC spiral, one of these wide spiral arms, all the bright stuff in the center is very relatively easy to see. All of these arms, which are very large and very spread out, means that brightness is getting spread out even more. And it makes it very, very difficult to see. So if you're looking at a 10th magnitude galaxy, for example, a 10th magnitude E0 galaxy, pretty easy to see in a smallish telescope. A 10th magnitude SC galaxy might be very difficult to see anything except the tiny little core, because the rest of it is so spread out that it disappears into the background. So knowing a little bit about things before you go out can give you a little bit of sense of what to look for and what to expect. So the spring sky, we have the Virgo cluster in the constellation of Virgo. It sort of stretches up into Coma Berenices here as well. So it's the Coma Virgo cluster right in this area. And if we sort of zoom in there, there's a whole bunch of galaxies, and they come in different groups. There's the Leo galaxies, and there's 5 of the Messier galaxies are in 2 little clusters, basically underneath the legs of Leo the lion. You've got a cluster of 3 Messier galaxies over here, and M95, 96, 105. And then over here, you've got M65, M66. There isn't a 3rd Messier galaxy there. I don't know how Messier missed it. There is a 3rd galaxy there, but it didn't make it into the Messier catalog, and so it's just got an NGC catalog. But so you've got these 3 galaxies in 2 different spots in Leo. And then the main Virgo cluster of galaxies. We'll take a look at just a few of these to give a sense of what they look like and what you can expect to see. Some of these images are actual drawings. Some of them are doctored photographs to make them look like my drawings, because I have a big sketchbook full of galaxies that I've been sketching for a long time, and somehow some of the pages have a lot of coffee on them. There was an accident one time late at night. So this is the Leo trio, M65, M66, and then NGC 3628 up near the top there. From my backyard, NGC 3628 is a little bit fainter. It is harder to see. And so maybe that's why Messier missed it. But the other 2 fit nicely into a field of view. This is a field of view of an 8-inch Dobsonian with a 25mm eyepiece, kind of a common visual telescope, low power field of view. So you can immediately tell that the galaxies are different shapes. We've got sort of a spiral here with a bar. There's some nice stars around it, a little L shape that makes it easy to identify. This other one's seen a little bit more at a lower angle. And then this one over here has a dust lane there. I've never seen that dust lane, very easily myself, but I know that other people have been able to see it at higher power. The Virgo cluster has, like I say, so many galaxies that you wind up just seeing a bunch of fuzzy spots, and it's difficult to track down what they are. These are two of the bright Messier galaxies, and they're surrounded by a bunch of NGC objects. And in this one field, you can really see some of the variety of the galactic zoo in terms of the different shapes and sizes and things like that. It's a beautiful place to look around with a good sized telescope from a dark sky. And this is part of an area called Markarian's chain. There's a chain of about a dozen galaxies that arc across the sky in that area there. This is a sketch I did of Markarian's chain back in, sometime a long time ago when we went to Texas. I forget when that was. 1832, something like that. And I was drawing in circles. You draw your circle and then you plot what you see in the eyepiece. And I realized that I was going outside the circle so often. So I stopped drawing circles and I just started drawing across a page. And I kept going until I ran out of paper. And I ran out of paper before I ran out of galaxies. So that was a fun night. It really is neat to track these things down and to see what kinds of differences you can detect with just the unaided eye. If you've got a tree in the way of the Virgo cluster, there's other great places to look for galaxies. We've got the Big Dipper. Easy place to find. Almost everybody can locate the Big Dipper. And surrounding that, there are a number of bright galaxies that you can track down. Two of my favorite galaxies are from the Big Dipper here. You sort of go crosswise across the bowl of the Dipper, and you go out about the same distance, and you end up at M81 and M82. Two wonderful galaxies, a beautiful spiral and an irregular kind of galaxy. Of course, the famous Whirlpool galaxy is just over here, M51, down below the tail. And there's lots of wonderful little galaxies in and around there. The Pinwheel galaxy up here, M101. If you take the Night Watch page for the Big Dipper, you've got a dozen galaxies that you can track down just on that page alone. So here's the Whirlpool galaxy. It's actually two galaxies, the spiral and then a tiny little galaxy that's being eaten by the spiral, essentially, as these two things gravitationally interact and over millions of years will change their shape. It's surprising that you can see the spiral structure like this of something that is so far away. Like I expect that I would see just a little spot, and in bad conditions, that's what you see. But once you start getting to a decent sight, and once you start practicing with your eye and really pushing your optics, you can see the spiral structure of another galaxy millions of light years away. I think that's really cool. The Sunflower galaxy, this is one that looks beautiful in photographs. You see a lot of people imaging it, and it's got all this glorious color and stuff like that. Visually, I find it really hard to get much out of. I think a lot of the detail is very, very faint and low contrast. It just kind of looks like a fuzzy oval with a bright spot in the middle to me, but I checked it off the list. So, sometimes, if you're a bird watcher or whatever, some of the birds are really cool to watch. Some of them you're only checking so that you can say you saw them. And for me, M63 is like that, but everyone has their own favorites. M64, the black eye galaxy, has that big dark spot near the core, which is pretty easily visible in small telescopes. That's something that's a good test of your eyesight. Once you track it down and you start looking, move your eye around the field of view. Don't just look right at it. And as you move around the field of view, you'll start to see more detail. Another tip for observing galaxies is, as you're looking through the field of view, knock on the telescope tube so that your telescope wiggles a little bit. And as it vibrates, that moving images triggers whatever the thing in our brain is that tells us to look out for something attacking us from the side or whatever. It triggers our peripheral vision and it gives us a better view. And sometimes you can see more detail that way. The Pinwheel Galaxy is another great one that is up near the handle of the Big Dipper. Really, really faint. The images look great because it's a glorious SC spiral, big spiral arms spread out. And you can see some little chunks of basically the equivalent of the Orion Nebula in another galaxy. But visually, it's really, really hard to see that kind of stuff because it is very, very faint and low contrast. Here's the M81, M82. Again, this is the sort of field of view you can expect in a typical Dobsonian. So about a degree field. And you can see, you know, here's M81 that doesn't look all that impressive visually. M82 actually looks like something's going on. We're seeing it from the edge and there's this dark lane that goes across and some clumpy bits. So it looks like something's going on in there. The images though show that M81 is this glorious spiral with wonderful spiral arms. It's something that I keep adding image time to every time I get a chance. I'll take a few more images and stack them in there. Not quite done with it yet. Need another 2 or 3 weeks of imaging time. Now there are thousands of these things and you can get as into it as you want, but I do recommend you get out and try and check out some galaxies because they really do push your visual observing. They're faint. They really reward someone that spends time and tries to observe carefully. Spend time looking at the eyepiece for a long time, make notes of what you see, because as you record it, it helps you to clarify it in your own head and it helps you actually see more. Try making a sketch. Doesn't have to be artwork, just the act of writing it down and putting it on paper and trying to convey it really makes your eye and your brain interrogate what you're looking at and you will see more detail in it. And hopefully you can absorb some of those photons that have traveled for those millions of years that made it through everything, including the clouds, because if we don't see them, they just hit the ground and it's a waste of time anyway. Thank you very much.
Anybody have any questions?
Scott, your view of 101
Yeah.
that you had up there, was that your sketch?
No, that was actually, I don't have what I feel is a presentable sketch of M101. So that is actually an image that I just changed the contrast.
No.
Many of those from your backyard, that kind of condition.
All of the images on the right side are from my backyard. The sketches were not from my backyard. The sketches were from either from Glen B or from Darker Suns. Yeah. So yeah, I don't have this artistic skill to sketch in white on black. I sketch on a piece of paper and then you just scan it and flip it and then it looks cool. It looks way better than it does on the other way around for some reason.
Want to talk a little bit about the power that you use, the normal power that you use to find?
Yeah.
Power that you use to observe, and then what you call higher power.
Yeah, that's a really good point. We didn't have a lot of time. So I like wide fields of view. I like to have a nice wide, like a degree field of view for finding things. And also because when you're looking at things in low magnification, it concentrates all the light into a smaller spot. It makes it brighter and easier to find the target. Once you're looking at it though, I like to bump up a little bit. I've got a 26 millimeter fossil as my wide field. And then I've got a 17 and a 13 that I will use. So basically about double the power. I don't like going very, very high though, because I find that galaxies don't really, in most cases, don't stand a lot of magnification before they just start to fade out. Although it depends. Depends on the night and so on.
So that's like 50, 100, and then
Yeah, 50.
200 power?
I usually don't go as high as 200. Often because I'm sketching and because I'm sketching from a Dobsonian, the more power you have, the more often you have to put the pencil down and move the scope, right? So it's laziness, to be honest.
What's your average? What's your aperture on the top?
I was using an 8 and a 10.
Okay, so
Can you get away limited than that. 25.
Oh, yeah, no, but I use Dobsonian just because it's sort of a common telescope, but any telescope that you've got will show some of those brighter galaxies. You can see all the Messier galaxies in a 3 or 4 inch telescope.
The best way of testing off your optics.
I can't tell you the best way of dusting off your optics. I'll tell you how I do it, and then you can listen to the gasps of horror from the experienced people. I have this camel hair paintbrush that I have never used for painting, and I tape it to a stick, and I put it down the tube, and very carefully I just brush it. I don't like to take the mirror out of my mirror cell, or even out of the tube if I don't have to. So that's all I do.
We're going to move on now. What I would suggest, if you've got additional questions for Scott at the break, track him down, and I'm sure he's more than willing to share the information with you. So I just don't want to double check. Was there anything on the chat?
Yes, Darren asked, any comments on binoculars and galaxy, Scott?
Yeah, I haven't had a whole lot of experience with binoculars and galaxies. I know the 80mm ones that I've looked through can show decent views, and I know there's a number of people that have basically 4 or 5 inch telescopes stuck together that make binoculars. So I think that those do very well. Your typical 7x50, it becomes more of a challenge just to find some of these objects because they are quite faint and quite small at that time. That's what I found.
Is that it, Judy? Yeah, I just wanted to give them an opportunity online as well. All right, we're going to continue on tonight with the main portion of our meeting. So we've just finished the beginner session. Again, thank you to Scott Young for that presentation. Again, Dennis Lyons, I'll be doing some of the hosting for tonight. We'll do announcements shortly. What's up will be with Brian Stack. What's new with Dr. Michelle Boyce. History of Glen Lee, a question and answer period with Jay Anderson. Then we'll have a break, and then our main presentation will be online, presented by our guest speaker tonight, Darren Hennig. And then afterwards, everyone's welcome to go over to the Boston Pizza on Pembina and join everyone. So, announcements. It's official. The RASC Winnipeg Centre is incorporated. Yay! And thank you to everyone who's worked on that, and all the members for voting to move forward with it. Thank you very much. Loaner Scope Coordinator, Mike Krackus. Scott already mentioned a little bit about it. Mike is in the room, I believe. For anybody who may not know Mike, he's the fellow you want to see. Again, if you're interested in boring or finding out what we have for scopes, please contact Mike or come see him at the break. First Fridays, Manitoba Museum, when we're doing it, Scott Young is coordinator, and he will let us know when we're going to do something down at the museum for First Fridays. Calendars, great news. Right before the meeting, it was decided they will be, if you're interested, they're $12 each. And you can see Abdul. Abdul's waving his hands over here, so we can see Abdul for that. Again, Winnipeg March, third Thursday. If you want to volunteer out there and assist when they have their astronomy night, the only condition is that you bring a scope for people to view through. Spring Tune-Up, March 25th, 1 to 4 at Eastview Community Church. And Darren Hennig and other volunteers of the RASC will assist members in getting their binoculars and their scopes and any of their other equipment tuned up. So it's a great opportunity. Please come out and support this. Because again, like Scott said, time to bring them out if they've been put away for the winter. Science Rendezvous is going to be, we're looking for volunteers on May 13th. Stan Runge is the one coordinating that. Stan Runge is over here for those in the room. Again, if you're interested, please see Stan. That's a University of Manitoba outreach event that we're supporting. NTANT is a new program that Damon Nightshade, Damon's here, I think. Damon, just hold your hand up here. Damon is coordinating that. If you're interested, it's a bit of an outreach program to spend some time with some campers and just to show them some of the night sky. Again, if you want more information, please contact Damon. Manitoba Education, we are participating with, they're looking at curriculum in the school and adding some of the science programs, in particular astronomy. We'll also be coordinating with Scott Young and the planetarium so that any things that we want to try and make sure it's a joint effort so that the same message goes across. It's a great, again, working with the planetarium is a great way to work with like-minded organizations. Same as supporting the Manitoba, University of Manitoba. Children's workshops. Kamala, is Kamala? I thought I saw Kamala is right here waving her hand down front. Kamala is our coordinator for that. If you're interested in assisting in some children's outreach workshops, please talk to Kamala and she'll give you some more information on it. Lockhart Planetarium, again, we're just mentioning that it opened in February 22nd. It's an opportunity again with the university. It's just another outreach for members to know about and to see. And a reminder about the RASC store that you can go to and get Winnipeg Centre merchandise. NOVA program, I'm going to talk briefly about this. We're looking at beginning a NOVA program, and NOVA stands for New Observers to Visual Astronomy. I'm going to see if it'll work. I'll take you to the link, and if not, I think that's a yes. I'll try a yes again, and if it doesn't, then we're no. So it doesn't like it. So there we go. Yeah, no closed current. Yeah. Sorry about that, folks. You just saw it. Give her a shot. So what it is, it's a program that's been around for a long time, but it's recently been updated. It's meant to actually bring people in and teach them all about astronomy at a different level. Each module includes student handouts. There's a slideshow that's already created and presented by members of the RASC, volunteers and staff. Interactive demonstrations or activities, optional observing sessions when applicable, and a resource list. So it's all about orientating yourself in the night sky, learning about constellations. And these are all different modules that are presented. So there's several in the program. And again, if you're interested in assisting to put this together, that's what we're looking for is volunteers who'd like to help. Because we need volunteers to make sure we've got volunteers to run the program before we're actually going to offer the program. And this is a program that will be open to not just members, but open to the public as well. Yeah, we haven't made that decision yet. Yeah, so what it is we're going to see if we get volunteers. So the council, as you can see, we've got a lot of different things going on, but the intent is not for the council to run everything. So if we think this is a good program or you'd like to volunteer with it, the council will support you to see that this activity actually happens in our center. Okay? That's why we haven't picked a date yet or set anything up. Yes.
Can you comment on the difference between this NOVA program and the Explore the Universe program?
Yes. So Explore the Universe program is meant to get everyone, the general public involved, including the general public, not just members of the RSC, involved in visual astronomy primarily. So the first program that Stan started having a meeting with some folks tonight is the intent between that is to take you out and using just straight your eyes and the binoculars, you pretty much can see and achieve all the things. And that program is meant to get you used to looking at the sky. So you kind of orient yourself. So when you walk out at night, you kind of can figure out where you are and what you've seen. There are some parts to it to try and, Scott alluded to that. And he said he did some sketching. Ideally, it doesn't have to be fancy, is that you sketch what you see. The neat thing about graphite pencil on paper is everybody looks like an artist. Okay. Okay. Some people are true artists. There's a few in the center that are really, really good. But everybody I've seen that tries it's good. And that's meant to help, and Scott alluded to it, is to get your eyes used to seeing what you're actually looking at. Not just a blob, what else is there, you know? And as you spend more time looking at the object, you tend to be able to pick out more details. So that's Explore the Universe. On the, very generically, is that fair, Stan? Yeah. Yeah. So, and then the NOVA program though, is to actually talk about, I don't know, I'm gonna use words that maybe I shouldn't, but cosmology, how the universe is made up. It goes into details about some of those areas. So there is some observing with it, but it's really learning about the universe. in a fun and interactive way is what it's meant to do. So one is really to get you to learn to observe and understand the night sky, where things are. And the other one is to get you to understand a little bit more about what you're looking at. Okay. I think I did okay. Groups.io. Now we know there's some people that are having challenges. We're going to try and put out a few different ways for people to get information, to know how to get on so that they can actually access the groups, because groups.io is our actual primary way of communicating. And if there's any subgroups, that's where those subgroups will be. So for instance, Stan will have an Explore the Universe in there. Darren Hennig has a subgroup that's for binocular use. So I'm not even going to try and click on it. But what happens is you would go to groups.io. This is one way. And then you would search for Winnipeg, RASC Winnipeg, and it will come up as one of the groups that you could log into. The other one there, this primary one, this, if you click on this group, it will take you directly to our main page. You still have to log in if you haven't already logged in. And then you there's some buttons on the side. You'll click or find a group. When you click on that, it opens up all the groups that you're either signed up to or could sign up to. So you would go to that area and click on the subgroups on the left side, and then you get to join what groups you like. So I would walk you through it, but I don't think it's going to let me link, because it didn't let me link on the last one. So that's just to let you know that there is a way to get in there. We will start sending out more information on how to get into the group and things like that through different methods. Members observing night, you've heard the weather forecast. It's not going to happen. It's just not going to happen. It got warm. Guess what happened? We got snow coming. Before we do what's up, oh no, I'll let Brian do his talking at that point. Does anybody have any questions from the audience or out in Zoom land? Pardon me? No, it wouldn't be on groups.io, but you can either deliver it online through Zoom. Oh, yes, yes. That information will get posted. Once we'll put out a call for volunteers on groups.io as well. Sorry, I misunderstood your question. Any other questions? Anything in the chat? Nope. All right, excellent. Then our next speaker, please welcome Brian Stack to do What's Up. Share screen. I don't see it here. Oh, there is. Okay, got it. Oh, let's go. You know, you should just hit 5. Yeah, but it's not. Let's try it this way. Yeah, just move that there. Slideshow. Oh. Yeah. There you go. Okay, at least it's up there. Okay, great. Hope everyone can hear me. Or not. There we go.
Not sure it's coming through on the.
Whatever works, it works. Okay. Hoping to have a duplicate screen. There we go. Okay, great. Okay, so okay, we've got this resolved. I think everyone can hear me. Welcome. We'll do what's up for March 2023. And we'll find out what's going on for this month. We're not. There we go. Oh, really? There we go.
We're using a different laptop because our regular laptop is homesick. Which one are you?
It started already.
Okay.
Okay. All right. Okay, so let's find out for what's up for March 2023. I'm trying something new, so hopefully this is going to work. I want a little bit more animation in my presentation. Right? There we go. Okay, let's try this again. Okay, for the planets. Okay, as for most of the planets are not going to be very visible during the month, they'll be mostly visible during the day. Mars would be probably the only planet that's going to be visible throughout the entire night. Venus, early evening, Jupiter too, early evening, but I'll talk a little bit more about it. Unfortunately, it's just going to be Mars for this month, but something special is going to happen with Mars. I hope everyone can see me. All right, so Mars events, a couple things we're going to point out, something I think relatively new. So of course we have the zodiacal lights that I keep mentioning every 6 months or so, one in the springtime and one in the fall time. What's special about this one in the spring is it happens in the early evening, so it makes it easier for everyone to have a look at it. I'll talk a little bit more about that later. Of course, we have the new moon on the 21st. A couple of planets with conjunction with the moon, and the first quarter of the moon would be on the 28th. So we'll talk a little bit more about what's going on. Okay, a lot of people at work were talking about, oh, did you see Venus and Jupiter? And yeah, so it's quite spectacular for those two planets. They're quite visible in the west side. Okay, and of course up here, I can't really see it. Is it there? Mars was supposed to be up there, but I can't see it. Is it? Okay. It's under the title right there. Okay. Now, what's special about this month is we have Mars, Betelgeuse, or Betelgeuse, depending upon how you want to say it, and Aldebaran that are going to form a near perfect equilateral triangle, but that's only during the mid-month of March. So as you can see here, we have, of course, Orion constellation. It'd be one of the main things that we can see. And I think it would be quite spectacular to see three bright objects. I think they're pretty well equal in brightness, but we'll have to wait and see. Again, it's happening mid-March. Over here, this is on the 23rd. We have, of course, Jupiter, we have the crescent moon and Venus. Now, what I'm going to try to do in the next slide, hopefully this is going to work. So what's nice about this part is, of course, we have the crescent moon with Venus. And it's going to happen in the early evening, so it'd be kind of nice to view it. Now, what I'm hoping to do, this is going to work. You can't see this. This doesn't come out very good, but with this new technology, I love my pen. There's the sun. All right, and right next we have Mercury. Highlighter right there. This took me a while to figure this out. I only have 2 seconds to do for each animation. All right, camera is off. Am I off? Okay, that's Jupiter is right there. Very nice. And of course, we have Venus. This is the following day from the 23rd. It's located right here. And of course, we still have the crescent moon located right down below. Saturn is way off to the side. I didn't want to make it too small of a screen, so I just left it like that. Okay, so March equinox is happening on
March the 20th. This is 4:24 p.m. local time for Winnipeg. So this is where we kind of get equal nights and equal days. So again, that's going to happen 4:24 p.m. on March the 20th, Winnipeg local time. Now, I keep mentioning this about these zodiacal lights. Next chance is going to be the fall time, but it's going to be in the early. The moon should not really interfere, but just wait maybe another week or so. Again, it's going to happen in the early evening, right after sunset. And I do have a picture and how it's going to look like. This is the zodiacal lights. It took me a while to figure out. It's bigger than what you think it is. And if you do get a chance, it's quite nice. It's got to be a dark sky. It's going to have to be away from the city. This was taken on my way to Arizona. I first saw it through Stan and Jay. That was really nice. It's quite spectacular. It's hard to look at it at first, but once you picture it. Now, what I'm going to do here is now that point kind of like follows the path of the sun. So right there would be the path of the sun. So it'll give you an idea where to look for it for these zodiacal lights. Okay, now the model here several times. I looked at the other ones too, and well, it's hard to say because I'm seeing here that it's going to be right here. It's going to be quite cold, but yet another model is showing only -8, and I put extreme cold. All right, but I looked at it again. It's not going to be that cold again. It's going to be -15. So I'm going to wait till Monday to see how this model is going to predict it. I looked at the model again just prior to coming here. Again, Saturday was supposed to be extreme cold, -25. As you can see here, it's going to be that cold, but it's probably the wind chill factor. All right. So precipitation, we have the cloud coverage here too. Of course, everyone, no big surprise. We're going to have snow tomorrow. And the only question is how much. I hear some people say 10 to 20 centimeters, but unfortunately, according to this model here, it keeps changing again. It was 5 centimeters last night. Today, now the model is saying 7 centimeters. So it's only a couple centimeters. But again, we are going to get more snow. So right here, that's Saturday, tomorrow. Now it says 5 centimeters, but now the model changed again to 7. So, and of course here we have more snow on the way. More snow, no big surprise for us. All right. As for clear skies, yeah, you can tell tomorrow, or yes, definitely tomorrow we're not going to have any kind of clear skies today. I looked at the model again for next week. We may have some clear skies around Saturday near 12 a.m. So we're gonna have to wait for that. So yeah, that was Thursday night, but that's not gonna happen again. So anyways, daylight savings time. Of course, it's a big talk on the radio and TV and all this. Everyone should get to know it. I'm still surprised that some people don't know it's happening this weekend. So it's happening March the 12th. Of course, it's always going to happen at 2 a.m. on Sunday morning. And of course, most gadgets nowadays, most of your phones are in computers, so you're going to switch over anyway. So we're going to lose 1 hour. So starting at 2 a.m., it's going to switch over to 3 a.m. And well, except for my stove and my microwave oven, I have to wake up and change the time, right? Because it's always going to show the incorrect time. All right, so that's all I have for what's up for March 2023. Thank you.
Brian,
Yeah.
just so you know that your camera won't switch over unless you allow it to connect to the internet. So if you're interested in keeping track of the
okay.
pictures that are
Choose
Yeah.
USB or USB-C.
update your camera.
Okay. Thanks.
We don't have
Thank
any
you very much,
USB
Brian.
ports is the problem.
And Judy, there was nothing on the chat?
There was a good comment that
Just drag it to
Darren
the,
made that you could shade the sun if you want to see
yeah.
the planets in the early evening,
Yeah.
late evening. And that it was interesting, Mike said that Betelgeuse, Aldebaran, and Mars are all red colored.
Yeah.
So it would be easy to see.
So we're just getting ready. Our next speaker is
Which one?
Dr.
This one
Michelle
right there?
Boyce. going to be talking to us about what's new.
Copy paste or whatever. Can't play it from the USB key.
No. Yeah, no
It's
problem. Just gotta get all these things out of here. Out of mouse.
There's always at least one little glitch.
Then eject, please.
Yeah. Just. There you go. Oh, no, it's still. in
Yeah, well,
use.
it's big. It's 164. It's got some
Oh.
zeros in there.
Okay.
Wait a second. Normally I get here on time.
Yeah, I'm just gonna have to pull that out because I need the mouse. Can't do this without the mouse.
Use the point points.
Yeah. Well, because we're broadcasting and we have cameras and things like that, right? So.
Yeah, just drag, yeah,
Oh, it says it's already here.
just for, either points there,
Yeah, okay,
just in case,
okay.
and
Okay.
eject.
Oops, not that.
Okay.
Yep.
Jeez. Might wanna plug that back in there.
There's a camera.
Play from start. Hey. Oh, yeah, play from start. Yeah,
Okay.
And
now we
we
just need
please
to share.
welcome Dr. Michelle Boyce.
We can put the microphone on.
test. Okay. So let's do what's new. Where's the advance? Uh-huh. Okay, so there's some interesting things going on with James Webb telescope because it's looking deeper into the universe. So they've detected, unexpectedly detected 6 massive galaxies in the early universe. These are about 500 to 700 million years old after the Big Bang. The universe is estimated to be around 13.7 billion years, and our galaxy is about 13 billion years old. And they seem to be detecting these large galaxies early on. And that doesn't quite make sense from what we understand cosmologically. This just shows our universe 13.7 billion years from now. And you can see that Hubble looks back to the Hubble Ultra Deep Field, and James Webb looks back to where we think the first stars are formed and the first galaxies. So we're expecting to see early galaxy formation. But James Webb is seeing these, it's seeing these galaxies that appear to be fairly massive and well developed. So this could end up turning cosmology on its head. It could change theories of gravity evolution. Maybe there was more star formation during the Dark Ages. So if we look at this diagram here, let's go back down. You can see you have the radiation era in the Dark Ages. And the Dark Ages basically, in the radiation era, it's almost like the sun. You have all this stuff that's, the universe is like a star, it's very hot, and then as it expands, it starts to cool and condense into gas, and it's supposed to be a long process during the Dark Ages, after which the stars start to form. and light up the early universe. So maybe what's happening is star formation is happening much sooner than later. But we shouldn't panic because this is preliminary data. There could be some other reason for it. So maybe just wait a bit, hang up our hats and wait a bit and see if this is truly the case. So this here is a video of how we think galaxies form. This is over a span of 13.7 billion years. And you can see, and this is over 100,000 light year view. And you can see how all these little forms, proto-galaxies, are slowly coming together, stripping each other apart and coalescing into larger structures. This is the formation of just a spiral structure. And this is happening since the early universe. So you could imagine that something like the Andromeda galaxy or our galaxy is being created over this long span of time. So you can sort of see now a spiral galaxy is forming. So basically, galaxies are sort of cannibalizing each other or coalescing to form different structures. And this just shows that one example. So you could imagine in the early universe of these small proto-galaxies, and slowly they interact and start eating each other and creating a final galaxy with large streamers. I think this should be over in a minute. I mean, it's 13.7 billion years in 2 minutes, so I can't really complain. Yeah, what's the hurry? But these simulations are, get better and better. But it really, so we simulate these things, and then we look back in the history, because light takes forever to get to us, and we say, does that look right for our model? I'm sure it's almost done. It is kind of cool to watch. You can find a lot of these videos online, usually at NASA or other university sites, and then they steal them, put them on YouTube, and then commercials. Anyway, I think we get the picture here. I think I was hoping it would end at some point. Oh, it looks like it is. But you can imagine how our galaxy, there we go. You can imagine how our galaxy was developed. And you see all these little globules there. So in our galaxy, we have what are called globular clusters. And those are on the outside of the galaxy. So you can kind of see how that happens and how you get streamers. LMC and the SMC clouds, they actually have a streamer that goes across the galaxy because they pass through our galaxy. So our galaxy has a lot of fossil history that is reminiscent of what we're seeing here. Then this is an article. Can people actually see behind this banner?
Yes.
Okay, just not here. It's a bit annoying, to be honest, but
You could move it.
does it? No, it should collapse. Oh, wait a minute. What's? Oh, lovely. There we go. Excellent. Okay, so as I mentioned, the universe is about 13.7 billion years old. And here Chandra found this lone early galaxy, 3C, third Cambridge catalog, 297, in the Virgo cluster. Now, yeah, it does look like a phone handle. Anyway, the problem with this is that it has all the hallmarks of a large galaxy cluster. And so normally galaxy clusters have lots of hot gas and dust, and which you can see in the X-ray. But here we just see lone galaxies. So we're asking, where did all those galaxies go? And it's theorized that they all got coalesced into one massive galaxy. And here you can see in this diagram, it's a composite image, and you can see the massive, supermassive black hole in the lonely galaxy. The other little blobs are foreground galaxies. And you can see this jet that goes to this hot spot, which is about 140,000 light years away from the black hole. Our galaxy is about 100,000 light years across, just to get an idea. And the Andromeda galaxy is about 4 billion years away, so it just gives you an idea. Light years. So the fact that we see all this interstellar medium and hot gas ignited in the X-rays leads us to believe that this was once a large cluster of galaxies. But that again brings into light the thing with the Hubble space, the James Webb Space Telescope that saw these massive early galaxies. Because this is saying that perhaps we don't quite understand the evolution of the universe. Perhaps the galaxies are developed more rapidly than we had thought. So this is yet another supporting piece of evidence for these new detections from the James Webb Telescope. And then the last subject, I wanted to go back to this Wolf-Rayet A star when I was showing all these James Webb Telescope pictures. And it was bugging me because I said, well, this is what a Wolf-Rayet A star was. And someone said, no, it's a binary system. So I look it up and I go, oh yeah, it's a binary system. And so what's happening, we have a Wolf-Rayet A star, which is about 10 times the mass of our sun, and a large O-type star, which is a very hot, big star, about 30 times the mass of our sun. And they're going around each other and spitting out material so each ring is about 10 years between a ring, like rings on a tree. So what's a Wolf-Rayet A star, first off? It's an extremely hot star. It's anywhere from 20,000 to 200,000 Celsius. At this point, it doesn't matter if Celsius is Kelvin, there's very little change. And our sun, just for contrast, is about 5,800 Kelvin. And here we see an example of a Wolf-Rayet 124. And you can see all this nebulosity around it because this star is so hot, so massive, so extreme, it literally is blowing itself apart. It's blowing off its outer layers, it's blowing off hydrogen cell, it's exposed heavy elements at its surface. So it has a very strong winds, high radiation output. So that's something to keep in mind. And it's a well-evolved star. So it's moved off the main sequence of stars. Main sequence is where a star, after it's born, sits and burns hydrogen for our sun, it'll be about 10 billion years, and then it starts to expand and so forth, and slowly become a white dwarf. So that's just to show the scale of the particular Wolf-Rayet star and the O-type star. And then I have another animation that shows how the dust rings. So there's the O star, the big one, and then the Wolf-Rayet. So this is that system. And you can see there, as they get close, there's such strong winds from the Wolf-Rayet star, they're getting blown off. Okay, and so this is an animation or a model of how those rings were developed. Okay, so that concludes my talk, and here's the end slide. I mean, we're talking about galaxies forming much earlier, but 22 billion years from now, we'll probably be ripped apart because we're accelerating. So something to look forward to, I guess. Anyway, any questions?
Yeah, can you go back to the one slide to that?
Animation?
Two things orbiting there, like this, I don't quite get this.
How they're orbiting?
Yeah.
So I'd like to do Do you know Pluto and Charon?
Yeah.
How they orbit about a single center of mass?
Yeah, but
Well, that's what's happening here. It's just they drew these lines that way. You can also draw lines. They're going about the center of mass, and you can actually draw the orbital lines. So the center of mass is in the middle of those two circles. Whoops.
Where the overlap is.
Yeah, right where the overlap is. See, you can see them moving together and in and out over the center of mass. It's just a different frame of reference.
yeah, that's weird.
Yeah, yeah,
Good question.
yeah.
So every ring is one period of the stars around.
Yes, so what's happening is, unfortunately, I was hoping that I could find an animation that would show it collecting.
Great.
But, so you have to imagine that dust is coming off and expanding, and in fact, if you look at the diagram, you do see a kind of an asymmetry.
Sorry. A ring every couple.
At 9.73 years, which is kind of an exact term when it comes to astronomy. It's usually a large error, so. But yeah, you can see there's sort of an asymmetry. So it's kind of being blown off in this way. And I assume there's a phase between the orbits.
How
So
far out do the rings go?
I do not know off the top of my head.
At least 100 years. 120
Oh, yeah, but it's not light years, it's whatever rate it's moving at, right?
years.
Probably hundreds of kilometers a second. So I don't think it's very large as the scale of things go. Yeah. Basically. Yeah, it's well, if I think of a solar system or Alpha Centauri, the core is about the size of Alpha Centauri, and then the rings come out, so you can get a sense. So it must be about, the core must be maybe light year across, and then probably several hundred light years, actually come to think of it. Yeah, okay. Any other questions? No? Okay, so that's it for what's new.
So that's in your slides, right?
So our next speaker is going to be Jay. And he's going to do a question and answer and give us some history of the Glenlee Observatory and then have a question and answer. And one of the reasons as Jay's coming up, a couple things first at break, there's a bunch of books up here. They're free for the taking. Please come up and help yourself. And one of the reasons we're looking at this is because we do need to spend some time this year. The council is looking at what we're going to do with Glenlee. So, and as far as a planetary observatory, what we decide to do with the observatory in the future. So Jay's agreed to give us a little bit of a history on it and then just field questions and hopefully provide some answers.
You're
to
welcome.
it. Okay.
Yeah, he's using the microphone.
Please welcome Jay Anderson.
Again, the only reason I'm up here is I'm the only one that's still left, except for Stan from those days, I think. Have to go back into 1977. Some of you weren't born, I should ask. How many of you weren't born in 1977? Well, we'll skip that stage.
I was born. There.
Just hit F. Okay, Glenlee. How many of you haven't been to Glenlee? Oh, I'm glad to see that. Oh, we got one here. Chris, time to take you down there. This is not quite what Glenlee looks like right now, but I'm gonna go back through the ages and talk about. Speak to me, old great computer. Okay, here's where it started. It started in 1923, actually. We purchased a brass refractor from one of the club members. I believe he decided he was getting too old to start using it, so we sold it to the club. I'm not certain that that isn't the telescope that Stan now owns. I'm not sure about that. 1948, there was a proposal to build an observatory by the then members of the RESC. And they wanted to put it on, well, two possible locations you can see there. And a pretty aggressive project too, was a 20-foot diameter dome, plus a fairly large garage-sized building to house equipment. Well, that would probably be 4 eyepieces, and I don't know what else they would put on it, but it was, in those days, telescopes were often sold with a little bit of a spectroscope. 63, Dr. Scatliff had an observatory south of St. Norbert. There's a big CKY transmitter there, and he had his observatory underneath that or on the grounds. He gave it to the RESC, but it wasn't really maintained and never really had a center telescope in it. It wasn't in operation when I got into Winnipeg in about 1974, or early 75. But in 73, they started to get serious about an observatory, and they had a raffle, raise $1,100. 74 and 75, they were looking for sites. And 76, they signed an agreement with the university to use the present site that we now have. Now, that project had trouble getting going. I was on council at that time, and we dilly-dallied a lot once we had this agreement, but nobody really got around to picking up a hammer and building anything. And Paul Moffat, who's still a member of the club, doesn't live in the city, so he doesn't come to the meetings very often, but you'll see him at Sprucewood Star Party. Paul Moffat rented a little shed, a storage shed like you have these days, bought all the lumber and built the walls, and then came to council and said, you have 1 month on the rental and all that stuff has to be out of it. Your walls are already made, so you better build yourself an observatory. At that point, everything went pretty quickly. We had some cement donated. They dug a hole and put a pier in it. You can see it's down 15 feet and up 9. We didn't go down low enough, actually. Then we poured the cement pad. That was kind of a half price deal, I think, from one of the local cement companies. Put the walls up, to hauled those out on flatbed and put them up. Didn't take very long. And then we built the dome on that, and that dome was built at Capyong Barracks. And Alan Dyer was a member of the club at that time, and his dad, Ed, was a carpenter. So Ed worked as a carpenter for the military, so he got permission for us to build the dome for this thing out of or inside one of the barracks or one of the work areas. Just going to do a quick cut. In one of our quests for where to put the observatory, there's a set of plans I came across, and they're looking for, let me just find a pointer here. If you recognize this site here, where they thought they might like to put the observatory, which was up in here, what we colloquially refer to as Garbage Hill, north of Polo Park. Probably a good idea. Give you an idea, here's the sign-in sheet for our meeting in 1976 in April. I've marked the 4 names actually, people who I know are still here. Paul Moffat at the top, Bill Crosney, and myself and Judy at the time. You might recognize some of the others in here. Here's Roy and Phyllis Belfield. Roy was the president at that time. He was actually quite involved in keeping the club going. He had put a lot of energy into it, and he had his own observatory in his backyard, and quite often after a meeting, we'd go and use his observatory with him. So This is a construction project of the original dome. You'll recognize a lot of part of it. I believe that's Roy on the left. Right here, I think this is Judy's brother, who never belonged to the club. And this is Roy and myself with the first telescope that went into that, which is the Dynoscope. Jerry, help me with this, 10-inch f9 or something like that?
It's a 10-inch, sure.
The tube for that is still in the university in their lost storage area by the planetarium. So that's a free press photograph. They did a little story on it. And here we are. This is Paul Moffat in the blue shirt here and also here. I believe this is Ed Dyer, but I'm not sure of that. And you'll notice we have the dome sitting beside it as we construct the wall for it. This is Ed standing on the dome structure that we built. It was covered in masonite, it was oiled. It was terrible material to build a dome out of it. It was an up and over door on it that didn't work very well. Great difficulty using it. It swelled in the rain and wouldn't move very well. Off on the right, I have Roy Belfield here with his back toward us, Richard Pachanko, who was quite a good interface with the university for us to help us get things and go through the process to get permission to use the site. Frank Shin in the background. I think Paul Moffat way in the back. And so here we are building this dome structure inside this big hall in Capillon Barracks. That's me when I had hair there on the right, or at least more hair. And so here's how the whole process came together. You'll notice that the warm room and the observatory were connected to each other at that time. It was one large building, but there was a solid wall between them, so heat from the warm room wouldn't be coming into the observatory area. It was all done with volunteer labor, and it went together pretty quickly, actually. I guess that's a duplicate. There was the first finished project. And you'll notice there on the right, there's a building there. That's the old university classroom that succumbed to the flood in 96 and 97. Although it took until about 2003 to remove it. It was a wonderful mold growth in there. We used to go in just to marvel at the stuff that was growing inside it. In those days, we were invincible, so we didn't bother to mask up or anything. Here's a bill for the largest part of it. Total costs $1,652.59. Never see that price again. 1986, put in a grant for the government with the provincial government. I asked for some money, did a little fundraising, and we bought the current ash dome that's on top of that observatory now. See, the total price for that was just under $10,000 American. I have a letter from the company that's part of this pleading with Stan to please send the final payment. Did they get it, Stan?
Here's the duty. I
Oh,
had
it's
to
a-
drive to the border to meet the guy to pay the duty to get it across. So that's what that.
So we're good with them.
So Jerry, we paid the bill.
We actually paid to have one of their staff come up and help us assemble this thing. So it was. Come on, speak to me. Well, then we got 96, and we got 97, and 2009, 96 and 97, 90, both of those floods got into the warm room. And you can see here, this is after but this is what the warm room looked like after the 96 flood. And there was even inside the university's classroom, there was a goose egg laid on one of the ledges by the blackboard. Well, there was nothing we could do with this thing. I mean, this is the cement floor. The wood is still in reasonably decent shape. You can see where the water level was right up past the electrical outlets there. Well, we got smart. First we took it all down. So here we are disassembling it. This is the warm room structure. We're now putting in a new base for a new warm room here, but you'll notice we've raised it up 3.5 feet. Determined not to have another flood in the warm room. The observatory itself was not so important because the observatory had nothing in the ground floor. There was no insulation or anything like that in it. So all that happened is the wood got wet and we dried out what parts we had. So at that point, we decided we would separate the two because we couldn't very well lift the observatory any higher. And so here's some of the work crew. You might recognize a few people there. This will be Kevin Black here. That might be Ray up here. Anyway, there are other pictures. And gradually we built the current structure. You can see it coming together in there. We started to rebuild after the 96 flood, but in the December 96, it became apparent that we were going to have a very heavy snowpack that year. So I suggested that they stop building in the early night or at the end of 96 and wait till after 97. And sure enough, the flood level was even higher in 97. So the existing building got soaked on 2 separate years. So here we are cladding it in and bringing it up to completion. It's pretty much done here. And we had a C8 at that time. I don't know when that was acquired. Was that coming when we got the new dome? Was that before that? Or it's not a C8, a C14. Yeah, anyway, that was the original telescope after the 97 rebuild that actually lingered into 98. You can see we're in the spring of 98 in this picture here. And that's a current shape of it. Of course, this building is now gone. And so what you see here is pretty much what we have now. Since that time, the warm room has gone through 3 floods that would have been in the old structure, but which didn't make it. Although one of the floods missed by about 1 inch from getting into the insulation under the floor in the warm room. So this last flood wasn't too much of a threat to the warm room, but it's now about the 6th flood that the observatory has had to endure. Here we are in 09. This is, you remember that this building here was flooded in 96 and 97. Here it is in 09 and it's still being flooded. It's stopped being used. It's all boarded up. It was a place where the university could store stuff like their telescopes that they used out on the pad. You can see the pad here has got piers for telescopes. At one point, there were telescopes in this building. It was all locked up, but we knew how to get into it at night when we needed things. So then in 2000, we put in the current Meade telescope. We wanted to get one that had electronics and computer control. And so that's the scope that's in there now, which most of you have seen and probably used a little bit. You can see the usual crowd of people. So here we are. We just had another flood. Here's what the bathroom looks like right now. This is me cleaning out the mud that collected underneath the warm room. It's actually quite easy to clean up because as long as you let it dry out completely, it sweeps up easily and vacuums at the end. So now the question is what do we do? Because we now know that the observatory floor is starting to deteriorate, and we've asked for a little bit of government money to fix that. We can do that fairly simply. Mike has sort of drawn up a set of plans and proposals that we could use. Want me to stop sharing? I don't know if you want to put the camera on me or not, but anyway, there are certain things we can do, like pull out the rotting 2x6s that are on the ground level of the observatory and replace them. We can do that without too much trouble. They're soft enough in some places now, you can probably push them out with your fingers. And then we'll put in new ones and we'll go on like that for probably, well, we had 45 years of it now. We could probably go on for another 25 or 30. One of the things we have to confront, though, really is that nobody uses the observatory. It hasn't been used all this winter. It probably gets used half a dozen times every year. And so there are other proposals to take the observatory down and put it at ground level so that it's a little bit more accessible to people. We could try raising it up like the university observatory over here, but then that brings us back to a complete reconstruction of the observatory, and it's not handicap useful. Certainly even healthy people have trouble climbing up some of those stairs sometimes to get into the current observatory. And we've had to be very careful about how we use it to avoid any liability that might come along if somebody falls down the stairs or something like that. So you'll notice that in the last few years, there's been quite a bit more support mechanisms, railing and things like that on the stairs to help people get up and down. Proposal I've liked is to take out the observatory completely and expand the warm room across the observatory area so that we have no observatory there, but instead just a bigger warm room. And then most of us go out there, we use our own equipment on the pad as it is. There's a 16 or 14-inch daub out there. I don't think that thing has moved for 10 years now. So,
It takes 3 people to move it.
yeah, it takes 3 people to move it. The fellow we bought it from had done let's say a Russian type job on it. He built it very, very heavy. It's absolutely solid, but it's it needs its own cart to move it. And unless you've been around long enough to know how it all goes together, you probably don't know how to put the finder on it and how to put the kind of like a guide scope on it. So it could be rebuilt to be a lot lighter, or it could be just sold off. Anyway, the question we want to throw out now, what do you want to do with it? I mean, plans are right now to repair it, bring it back to the way it was. We don't have a problem with the warm room. We have to do some construction on the bathroom. The bathroom was going to get flooded every time that it floods because it's at ground level. So it's just a price we have to pay for, you know, relatively infrequent floods. 45 years, about 6 floods, maybe 7. So we'll go about every 7 years or 6 years when we flood again. How often do you want to rebuild the bathroom?
What's the budget?
What's the budget? I don't know what, there is no budget, but we have got a government grant application out. We have reason to believe they'll give us some, but that's to repair the existing structure. That's not to. The budget can be quite small depending on the project, but I would guess that to extend the warm room, I don't know, 20, 30,000, maybe less. I don't think that's beyond our capabilities. The thing to do now is get some ideas of what you'd like to do. And then we'll see what we need to do to achieve them. Raising, I mean, we did get $10,000 from the provincial government. RSC National has a fundraising coordinator who, if we can make this thing in some way accommodate handicapped, then there is government money available. That's, I don't think the kind of money we're talking about is a really big problem here. Question of what would we use?
I'm wondering if we know whether the observatory is not used because no one wants to use it, or because the observatory is not used because it's not user-friendly and accessible, and people can't easily get trained, and things like that. I remember when I joined specifically because like C14. And that was a huge part of the
Yeah,
membership.
that was a big telescope, but,
Yeah.
and I remember using that old C14. You know, there was no reason why with some of the lovely planetary conjunctions we had, anybody couldn't have gone out and turned the mead and looked at them. I mean, it was there, that comet that was here, you could have gone out, you don't have to bring your own equipment, you don't even have to worry about the cold, you just go out there. And once you know how to run it, 15 minutes on the mead, you're looking at the comet. Nobody did.
Somebody from the zoo says they've been in the club 5 years. This is Robin Clark. And only went to Glenley once. It's not as dark as other areas around it. It's prone to exposure from water. It would be costly to maintain going forward if it's not going to be used.
He's exactly right. Something that we are limited in when the road is very soft, because that road has been in need of gravel now for quite a long time. Stan and I used to go out onto the access road by the highway and steal gravel off of it, put it back and dump it into the holes. But there's only so much you can do when you really want 4 dump truck loads of it. Can't fit that much in the back of your van. So these are other considerations. But let me point out one thing right away. Glenley is darker than any place in the city. It's darker than any place north of the city until you're past Birds Hill Park. So if we set it up into something that somebody will use a little more, like I like to go to get Glenley once in a while and just have a lunch out there because it's a nice, pleasant place with tables and microwaves and kettles and a bathroom and that, and so you can have a picnic out there. Of course, we have one club thing. But those are limitations. The fact that Glenley is not always accessible. Usually you can get to it in the winter. There are times when there's a little bit of a drift, but usually the farm will look after that for us if we contact them. The worst time is in the spring.
Actually, they clean it regularly now because I got in contact with the people that do it. Also, in terms of usage, I go out lately a lot in the summer. Quite a few people pop in and out, so they do like to use that area. I've always been wanting to use the larger scope on occasion, but I've never been properly trained on it. So I'm afraid to use the equipment. As far as the size of the war room is concerned, I think it's fine because I've been out there when there's lots of people and it seems to be an adequate amount of space. And in terms of repairs, it doesn't seem like it would cost much just to fix it. And it should last for some time before we really have to make some serious decision. I have thought that maybe there's some kind of liner you could put in the dome to prevent further flooding and perhaps raise the toilet. I'm not sure how big the roof is. So.
Yeah, toilets can't be raised because there's a laser here with the dome.
Yeah,
and the
that's what I
location.
figured. Yeah.
So that's a problem there.
There was a discussion of a roll-off, like observatory, so if you have scopes, actual scopes, somewhere on the other side, it would be a roll-off thing where you just roll it off, and use that 16-inch or whatever.
Yeah,
Anyway,
the status quo is completely viable.
Yeah.
Position to take on this, just repair what we've got, and keep on doing what we're doing.
Yeah,
The war room got a major cleanup. It was becoming a junk storage area. Awful lot of stuff got thrown away. So it's a little more comfortable to be in now. There are people who will go up to Glenley and stay overnight and sleep in the warm room. And then go home once they got a little more cognition in the morning after a few hours sleep. A bigger one might allow that. We used to plan on actually having meetings out there occasionally, but that was when the club had 25 people in it, not 225. Judy,
A couple of people on Zoom are saying that they think we need a dark sky site with a warm room and a washroom. And most people use their own scopes when they go to Glenwood. And then another person, I think it was Darren, suggested moving the observatory to somewhere else. And was that feasible?
yes and no. Now, we've had offers on a dark sky site down past St. Malo. Who's gonna drive 2 hours to go to a dark sky site? We wouldn't own the land that it's on. That's one of the things. The university pretty much lets us do what we want, as long as we maintain the property and we keep it insured. And so there's been a lot of discussion. I offered the club a 1 acre site to the east of the city out near Vivian that they can have for a buck as a dark sky site. But again, you know, if we can't get people to use Glenley, then you end up going to dark sky sites sort of ad hoc. You know, in the past, we used to go up to Sid's Corner quite a bit to use the dark skies up there. There's Sprucewood Star Party, which has got some pretty good dark skies in it. So yes, the big problem with the dark sky site is finding the land and having a certain amount of independence. In the past, we've scouted quite a few places in southern Manitoba that would not be too far from the city. If we drew a 1 hour radius around the city for finding a dark sky site, you have very few options. You have to draw a 2 hour circle to get into dark skies. The only dark skies in southern Manitoba are in the southwest near the border and in the southeast near the border. Southeast is probably not as favorable for the weather as the southwest. Other than that, you're going a long way north. But anyway, it's something that we could look at.
I don't know if this is done before, and is it possible to, because people now use their own equipment more, is it possible to set up some lockers for members to store their equipment there, and then maybe set up a rental fee to support the maintenance of the observatory? And because in my own country, my society did that, trying to do that one time, and quite a few members do that. I mean, that location a lot because they just go there and then don't need to pay. Don't need to.
Let's see, Scott, would you like to answer that?
I would love to see something like that. There was for a while a bit of a problem of people leaving their stuff in the warm room. And then you would get there and the couch was full of somebody's refractor or things like that. So it was a problem, but it would be nice if there were storage out there. I would love to be able to leave here and just drive out there and not have to load the car. And things like that.
I think the site is quite dark and close to the city.
Yeah.
And moreover, if the
Want to wrap this?
usable,
Yeah.
I would go a lot. I mean,
The washroom was a big deal for a lot of people for sure. You know, to the extent you're enduring your out there. As opposed to going to, maybe a darker sky site.
Okay, we're getting low on time here. I just draw your attention to this thing here. This was my observatory on the pad that lasted there for several years.
Cliff asked if it's possible to build up the elevation around Glenwood to make it floodproof.
Well, you'd have to build a dike around it. The university would have to do that. So we could probably ask, but they are relatively floodproof now, although a 96 level flood does get into the university observatory, 97 level flood. It'll get about a foot.
Another person suggested that we share the university's facilities and build it closer to that dome so that we're a little bit higher ground.
The best thing we could get from the university is internet access. But now most of us have cell phones that can do that anyway. Anyway, I think we're out of time. Dennis is looking at me with daggers in his eye now. Think about it. send your suggestions to me or just put it in for discussion.
Thank you very much, Jay.
That is me.
So we're gonna take a 15-minute break and start back at 9 o'clock. And again, just to follow on this, if you've got ideas and thoughts, there's been lots of good ideas put out. If you can send it to one of the council members or myself, Dennis Lyons, that would be greatly appreciated, because again, we're trying to look at all the different options and try to make the facility either user-friendly or determine what we actually need. So we'll start up again at 9 o'clock for our guest speaker tonight. Thank you very much.
Yeah, exactly. Thank you. Beginnings of an interesting conversation. Eh?
Oh, yeah. And just a reminder, there's lots of books up here. Please help yourself. I don't know who that is.
Genetics,
Oh, is it? Oh, okay.
genetics.
Hey, I'm not too
So
bad.
Darren is gonna zoom in.
Yep. Oh, that's,
So
okay. I'm sure Scott. We'll get that figured
Oh,
out.
hey, look at that.
one
That's
thing
pretty
I've
sweet.
never done is
And then this is the disc
to
that they
get
have with
to
it.
the chat.
Okay.
The chat has a whole bunch more.
Chat should also be.
Take a look.
Yeah,
Yeah,
That's
I think
awesome.
it
Okay.
Yeah.
You're coming
That's
for
what I've
Crystal?
always
No.
understood.
Yeah,
Oh,
Chat's
so
always good.
it would be useful to write out a
Okay.
little bit of the questions that were asked about.
yes, it is. Yes, it is.
Because,
Yeah.
you
Okay.
know, those are
Oh, that's too bad.
exactly the things we
And then
think
the
about.
thing with you is,
all the time.
that I want to talk about,
Round and around in
with
circles,
the,
right?
sport universe,
So
how to
if the
do that,
university
if people could,
would really put their heart.
we could
and soul
separate those outside.
do something
One
out
shared
there.
message.
Yeah.
At least it would be a place for
So
plans.
the ones that are on the city, you
If
can put on
the
the
university
IO
is
group, and the ones outside, whatever you want to stimulate.
Yeah.
then we pretty much
Is
have
there-
to do the
I was
other
thinking,
thing.
well,
But if we own
just, we could just start another group,
other
.io. And then, I don't know if there's a way to do forwarding between things or whatever, but that way it is, we don't wanna give non-members access to our stuff.
We need to
Right, they gotta be
figure out
separate.
people.
Yes.
Yeah.
And then
So that's
that
the
becomes-
thought process.
Yeah, okay, that's cool.
And I
You
thought,
know, it's.
yeah, you know how to delineate
Yeah.
it. You've got
Well,
to
in theory,
And
Figure out a way
one
better
person
than I
did
do.
say that.
Okay,
their
no, that would be good,
problem
that would be
was
good.
that the training
Okay.
wasn't available, which.
cool.
And then we get together, yeah.
Yeah.
I don't know what day is the best for you next week.
Next week is,
If you're downtown,
we can do what?
sushi.
Yeah. Well, I will come downtown for sushi. I will come downtown for sushi. There's, I think Tuesday I'll be downtown for sure, and maybe Thursday as well. So,
Okay, all right, so.
yeah,
I'll
send you an email. Yeah,
I'll be
we'll-
back.
yeah.
They can't use it forever because.
I don't know.
They're just storing
Black something, isn't it? It's called black something.
Yeah. The melanite. The melanite, right? Yes. I thought it even had the word.
No, I just. I have something.
Yeah.
So let's see.
That makes sense.
That's why that's.
Oh, you haven't got that yet, right? Yeah, just email me. And I will send you back the information. Myers is the right name. I was not sure exactly how it's She had to go off and buy the extra. Now, she wouldn't be without her. Especially because the virus was not as dark as the stock part of that. So the individual, right?
All right, folks, we're gonna get started here in just a moment, so if you please make your way back to your seats. Evening, Brian. Good, good. Yep.
So I did it before, I'll be the judge.
Perfect. Yeah, so just make sure you write down the name and send them the name so we know the check, who got the check. Perfect. Excellent. Thank you very much. Well, if you're like me, man, I take them all the time. Okay, we're gonna get started here. Again, folks, we're just gonna get started here. Yeah, I know, there's lots of books. You can come get books. Lots of books, shiny books. So I'm going to introduce our next speaker, and Scott, not quite ready yet. So again, our last speaker there talked about Glen Lee and possibilities of what we could be looking at. So again, it's what the council hopes to do is look at what we could be doing, come up with a plan. Somebody earlier had asked about what was the budget for it. Well, really, once we know what we want to do, then we'll be able to figure out, determine a budget, build a project plan, and then go from there. So Darren's ready. Okay, so we're just doing the final touches here. I'm going to introduce our guest speaker, and our guest. That's okay. And our guest speaker tonight is Darren Hennig, and his title of his talk tonight is Double Trouble: The Joys of Observing Double and Multiple Stars. Please welcome Darren Hennig.
Thanks, Dennis. Can everybody hear me okay? So far, so good? Hello? What's going on here? Okay, loud and clear on Zoom. Okay, excellent, excellent. I'll share my screen here. Let me just flip to my presentation here and we'll get going here. So thanks everybody for attending. I just have a couple of super quick announcements that I just wanted to add before I get started. I'll just take a quick minute here. Let me just maximize this. So as you know, I head the Binocular Observers Group, and just so for those of you that don't know, I'm going to be moving to Edmonton at the end of the spring season. I will attend the session next month in person, so I get to say my happy goodbyes and unfortunate parting words there for some of you that are attending in person next month. I really enjoyed being part of the group here, and hopefully I'll be able to once in a while pop in as maybe a guest speaker on invitation. I'll stay in touch with many of the friends I've made here. Just so that you know, James Fast has volunteered to take over as Binocular Observers Group leader, and I'll make arrangements with Russ to have him in the next month or so transition to be the leader of the group, so that way when I depart, then he can do that. So it's with a sad moment that I'm going to be leaving a lot of good friends out here, but I'll be thinking of you fondly. I also wanted to just mention a little bit about this spring tune-up event, super quick. As Dennis mentioned, it's Eastview Community Church there on Maxwell King Drive. And it's going to be going from 1 to 4 p.m. And we'll also have an optional social event after the tune-up event. We'll be doing an announcement on the general forum shortly. James and I are just working out the details for this. It's not just for the Binocular group, it's for anybody that wants to bring their instruments to do things. We might even do a swap and shop. I'll discuss with our executive whether that's even viable or if it's a good idea. And if anybody wants to volunteer to assist us, I've already got about 4 or 5 more senior members, and thank you for your indications of doing that. We're going to have some modules there as well, so I think it'll be a lot of fun, and hopefully the weather will be nice. Maybe we can do some solar viewing and stuff too if the weather's good. We'll have refreshments available as well, and hopefully it'll be a lot of fun. So look forward to seeing you there. So let me just get out of that one and I'll get my main talk going. Thank you for the intro there, Dennis. All right, so today I'm going to be talking about double trouble, I called it, understanding and observing sibling stellar systems. And this is one area that I really enjoy doing personally. And as some of these topics that I picked for my talks, they're multifaceted and usually delve a lot deeper. You can go in rabbit holes in several directions. So I'm just going to do a broad overview on some of this for the group here tonight, and hopefully wet your whistle on some interesting areas of double stars. And interestingly enough, Michelle's talk about the Wolf-Rayet star, their WR124 with that binary system, is a nice segue into later on this talk as well. So don't worry, I'm going to have a little bit of math, but nothing too extreme to show you. And we won't certainly be doing any sort of, advanced astrodynamics or anything like that. But I will just do a broad overview on a few things that'll be nice and relevant here. So what are double and multiple stars? Well, basically, these are pairs or sibling stars. They could be their systems as complex as 6 and 8 stars in the same system that are orbitally and gravitationally bound. And during the stellar evolution in the protostellar disk, we can get differentiation, agglomeration, and technically. Oh, yes. Is there a problem?
Yeah, you're sharing the wrong screen.
I'm sorry?
You're sharing the wrong screen. We're
Oh,
still seeing the tune-up slide.
oh, my apologies. I didn't realize that. Okay, let's try this. Is that better?
Yes.
My apologies. So let me just go back one here. You haven't missed anything really yet. So I just said there's some math in here, and we're going to be talking about, I'm not going to get too heavy in the math because we have a fairly broad audience. So what are double and multiple stars? Well, these are pairs and siblings that form during stellar evolution from a protostellar gas cloud, and you get differentiation and agglomeration and even accretion. And depending on the variable density that you have in this region of gas, we can get more than one star forming. And there are systems that are even as large as have 6 and 7 and even 8 stars associated with them. They're gravitationally bound, sharing a common orbital momentum. And they aren't necessarily always twins. As you see in this slide here, sometimes they will have different spectral characteristics as well. Not all multiples are that are visible or bound. Some are chance alignments. I'll talk about that a little later on when we start talking about how to observe some of these types of systems. And they're both fun to photograph and observe, and some even have exoplanets. That's a talk unto itself, so I'm just going to do a very broad overview on that near the end of this portion before I get into how to look at these and where they're found. But I thought it would be important given that we're starting to see exoplanets around these multiple star systems as well. So normally when I do a talk, I always go back historically, although I'm not going to go as far back as I have in the past. I'm just going to kind of start at the advent of where the telescope was available as an optical instrument to assist us in viewing. But we're going to look at some of these contributors to the study of these very interesting systems. Now, on this slide here, you can see part of the Big Dipper here in Ursa Major. It's cut off the handle, but one of the first, it's no surprise that during the advent of having a telescope available for observing the heavens, that close stars were obvious targets, and some of the, obviously Galileo and one of the other earlier astronomers using a telescope, Castelli in Italy, noticed that Mizar looked to be a double. So in other words, they saw Mizar and Alcor, but then when they trained a telescope, they could see it was also, Mizar was also a double as well. So they saw 3 stars in the sky. Shortly thereafter, of course, you have Robert Hooke, an English scientist that discovered one of the first other double star systems in a different region of the sky, Gamma Auritus, in 1664. The bright southern star in the Southern Cross, known as A Crux, was also found to be a double by a French astronomer, Fontenay, in 1685. Since that time, there's been many searches being carried forward throughout the entire sky. And double stars down to the primary being a limiting magnitude of 9 have easily been carried out. And this involves hundreds of thousands of systems throughout the sky. An interesting factoid here is at least 1 in 18 stars brighter than 9th magnitude in the northern half of the sky are known to be true double stars, visible with, even as large as a 36-inch telescope. Now, when I say this, this means that the secondaries could be substantially dimmer than 9th magnitude, just so you know. But this will have some consequences when I talk about the statistics of finding multiple stars in the sky. For those members that have joined more recently or are just getting to learn the sky, I thought I would just show the Big Dipper again. And so when I first talked about Galileo and Castelli seeing Mizar, this is the bend of the Big Dipper, and this is a better slide here to show where they're located. I just thought I'd show that for people so that the new members can understand, one of the earlier stars that were studied. Now, this will get into two prominent families that really sort of pioneered the work carried forward from earlier researchers, and William Herschel of Uranus discovery fame also began a survey to look at doubles. Actually, it started out as trying to measure stellar parallaxes and try to determine stellar distances. And he noticed that when he was looking at some of these double stars or close pairings of stars, he noticed the parallaxes correlated, so therefore they must have been associated with each other. And he found that the speculation was these must be in mutual orbits. At this time, of course, this is about 100 years after Newton's theory of gravity. So, and of course, Keplerian treatments of planetary orbits. So this could be extended to these systems as well. So we're talking, less than 150 years or say 100 years or so, and they're already looking at these. Now, he himself, during this parallactic survey, found over 700 double stars on his own. And of course, the Herschel family, including his sister Carolyn and his son John, collectively cataloged over 10,000 double and multiple systems. And many of these in the later years that John was doing the work, he pioneered modern binary star astronomy, and a lot of these were starting to also be photographed to try and discern the relationship of these stars in their mutual orbits. And of course, photography at the time was fairly new, but it was applied fairly readily to these systems. Another prominent family that was also very instrumental in cataloging and studying double stars are the Struves. Actually, 3 generations of them, but 2 prominent ones that were kind of in the same time frame as William and his son John, particularly his son John, is the Struve family. And these were German astronomers that were involved in studying quite a wide range of astronomical objects, but one of their bigger claim to fame was to extend and enhance the catalog stars that the Herschels had started. And of course, the son Otto von Struve did a lot of astrometric studies and refined orbits of binary stars and orbit types as well, moving forward. So we have 2 families that did a lot. Now, obviously, after these 2 families, there was many other contributors, Burnham near the early 20th century, and many others, Dunlop from England, and so on. But this really sort of lit the match, if you were to lit the fuse to get going on what these systems can have to offer. So we'll move into the bulk of what we're going to talk about here. Binary and multiple star facts. Well, I know I said 1 in 18 in the Northern Hemisphere are true doubles, but current research has actually found more recently that on the low end, almost about a third to as high as potentially half the stars in the sky collectively could be associated with multiple star systems, not just doubles, but maybe triples, quadruples, and so on, sextuples. And that's in our galaxy. So that's well over 100 billion stars potentially could be associated with multiple systems. That's quite a few. So they're very, very prevalent throughout the cosmos, at least in our galaxy, and certainly probably other galaxies too. These are also mainly sampled from main sequence star populations, but not exclusively. There have been binary pulsars and other more esoteric systems. I'll talk about a few of them tonight. I won't touch on the Wolf-Rayet star systems, but Michelle did a nice little segue already, as I mentioned. The binary orbits can be used to define stellar masses of the pair, and I'll go just briefly on the procedure and how that's done. And also, binary stars are associated with certain novae, and in some more extreme cases where you have more energetic systems and more perturbed systems, you can get a class 1 supernova, and I'll talk a little bit about how those happen. That's related to the Wolf-Rayet type scenario a little bit. Binaries can also be used to refine exoplanet data in the case where a suspected planet might be present in one of these systems. And we'll talk a little bit about exoplanets and where we might find them around multiple systems as well. So there's a lot to talk about tonight, and I'll try to keep this moving fairly well. But as I mentioned before, you know, when you look at the statistics of these double star systems and multiple star systems, you can see as you go from a primary of about 0.1 solar masses or just slightly under, and as we get to larger systems where you have, let's say, 16 solar masses for the primary, the probability of having an associated partner or more than one associated partner goes up quite substantially. If you think about this, this really makes sense, because if you look at the protostellar gas cloud, if you have a lot of mass, you have the likelihood of having more than one star form, right? Rather than if you can barely make a solar mass worth of star, then the chances are there's not as much material left over to have another star. That doesn't mean that in the case of the lower mass range that you can't have binaries that are fairly light. Like as an example, there are some star systems that are binary brown dwarfs as an example. They didn't quite get to the fusion stage, but they're sitting there orbiting each other. So this is a very interesting fact, and or an interesting correlation here. It makes a lot of sense when you think about it. So basically, as I mentioned before, we have let's say some sort of a protostellar disk or gas cloud. And these are just simple diagrams just to make the concept known. As we start seeing density changes, not unlike what happens in what we think might happen for planetary systems, if there's enough mass, you may get enough material accreting to form multiple stars. And in the lower portion of this slide here, you can see that in some cases, you might have multiple stars where as they're forming and as they condense and start igniting and forming fusion, they may end up shifting orbits a little bit during their early evolution before they finalize their orbits. So again, this is not dissimilar to some of the modern theories that we have for planetary system formation as well around a solitary star like the sun. So this type of orbital dynamics is fairly universal. Now, when we look at actual stars in the sky, of course, there's a strong correlation between intrinsic brightness and temperature and luminosity. And usually we use spectroscopy to discern how hot a star will be. And in this case, as you see a larger and larger, and astrometry too, of course. So as you see a brighter star and more prominent lines, we can discern the color temperature of the star. And on the left-hand side of this slide, these are the main categories for spectral type versus color. And you can see as you go down the list that they get cooler and cooler. And of course, other spectral features will be prevalent. The important thing to remember here, and I just minimize that a little bit to show the Hertzsprung-Russell diagram. And as I was talking about main sequence stars, you can see that a lot of these stellar populations that are studied, we don't have time to, this is a topic unto itself, of course, but you can see the population of stars and they tend to follow certain patterns here. And you can see the color, the color which relates to the temperature basically, and the luminosity. And of course, in the case of the sun, we use the sun as one, as unity for that. So this is another way of looking at the Hertzsprung-Russell diagram. And you can see, the different branches off. Obviously, some of the more energetic and extreme stars will fall outside of these, like the Wolf-Rayet stars and some of the hypergiants and so on. But there is still a fairly good correlation along the main sequence and even into the subgiants and some of the giants, where you get a correlation of magnitude versus mass, say, or brightness versus mass. So along the main sequence, there's actually a fairly strong correlation between luminosity and mass. And we can utilize this to understand these double star systems as well. Because if I look at a population of stars here, you can see the surface temperature is related to luminosity. And if we do a log plot of luminosity and what we know for masses of stars now currently, it's a fairly linear plot, at least for the bulk of the stellar population within our galaxy, or the observable stars that we have. We can utilize this then to estimate the masses of even a binary component. When we see it, we can take the spectra and discern the both the brightness and luminosity as well as the masses. And the nice thing is, when we're looking at these types of systems, then we can discern a little bit about the characteristic of the orbit. Now, obviously, these are just sort of very simplistic systems, but you can see everything from, let's say, a true twin system where you either have a near circular shared orbit to a mutual elliptic orbit around what is called the barycenter, or the center of mass. And of course, in the case where you have systems where the two components have quite substantially different mass, obviously the motions will be more for the lighter component. You think of it like a teeter-totter, where if you have a child, you don't need necessarily to have you need to have a longer fulcrum in order to balance it with an adult, say, as an example. So when you're looking at this dance around the center of mass, this is what we're talking about here. Now, just keep that in mind here as I go forward. So when we look at these orbits, this is an example. This is a website that you can actually get these kind of diagrams from. And the Gibson Smith has about, I would say 150, I think it is, double stars or multiple stars where it has the orbits characterized. You can see 70 Ophiuchi here has a just under a 90-year period. If you look on the map here, sometimes what we'll do is this is what we call an apparent orbital diagram. So this would be the orbit relative to having the primary or heavier, brighter component right at the center of the diagram, or in this case at the origin, and then the minor component is orbiting around it. And we can see over time, we can trace the position relative to the primary, and we get an idea of the orbit. And here's another example. Here's Xi Ursa Majoris. It has a smaller period, and there's no doubt that you can see it change a little faster. We're getting close to periastron for this system, and you can see here with the scale, it's a little closer into its primary, and secondary spacing is a little closer than in the other one. But there's a whole wealth of these. Now, having said that, with these diagrams, I will talk as to why we'll be using those later. So we can use these binary systems as we prescribe the orbits to eventually translate to understanding where they are relative to each other and their respective orbits and how eccentric they are. And using Kepler's equations, we can actually plug in the total mass of the system and be able to get some of the information, like the distance between the two stars, is measurable and observable, as well as the period for one orbit. The only problem is we don't know exactly what the masses are. Now, using the mass-luminosity relationship, we can get an estimate, but there are other ways to discern the mass as well. And watching these stars dance around each other is an excellent way to do so. Once we have these stellar masses, we can then plug them into the center of mass equation. I mentioned teeter-totter or fulcrum, and we can actually get the two masses. The nice thing is with these systems is they also help to cross-correlate the luminosity mass relationship estimates and refine the current theories. Usually in cases of star systems like this, especially where you have a large difference between stars, like a very massive star and a very light star, the lighter star will be moving fairly quickly, and relativistic effects come into play. And I didn't want to get complicated with relativity in here, but you get the basic concept. Very interesting. Now, I'm going to just talk on how we do this translation very briefly, and I'm not going to go into the mathematical transformations that you do to actually get the absolute orbit down below. Here's an example of Alpha Centauri, and you can see the apparent trajectory is very similar to those two slides that I had for 70 Ophiuchi and Xi Ursa Majoris. In this case, we're seeing the star system fairly obliquely. When we do the first transformation here, once we translate the apparent orbit, we go to the middle section here where we get what's called a relative orbit. And that's where you get the flattened, the flat edge on or straight on ellipse, as if we were orthogonally viewing the system from the perspective of having the primary at one of the foci of the elliptical orbit of the secondary. And you can see how these would correlate. And then with further mathematical reconstruction and geometric manipulation, we can actually get the binary orbit calculated out. And that's what you would plug into those equations to get the respective masses. So a little bit of mathematics, certainly beyond the purview of this talk tonight. But for those of you that are interested, you can certainly, there's lots of information online on these. And you can dive into it and cut your teeth if you really enjoy doing a lot of fancy geometrics and mathematics. But this is basically the procedure that they use to determine that. And that's why it's very important to have this orbit at least well characterized so that you can get these mass estimates. Now, in an extreme case, we have, like when I showed you the slide with Alpha Centauri, AB, you have a fairly oblique view, but in an extreme case where we have an edge-on view, we can't see the orbit very easily. So now we would have the likelihood of the stars now crossing each other in a mutual eclipse at periods of time. And so this is like kind of a stellar peekaboo event, I guess you could call it. Two very well-known eclipsing variables or eclipsing systems here. Algol is very well known, and you can see on the bottom right, basically what happens is as these stars mutually eclipse each other, you'll get a brightness change. A very significant one is the smaller one gets occluded by the larger one. And then, of course, the other one won't be necessarily quite as deep. And it depends on the relationship between the two stars, both their intrinsic brightness and mass, of course, as well as their size. So you can get quite a wide range of different light curves on here. Algol obviously has a smaller secondary eclipse, versus the primary eclipse is quite deep. SV Camellia Pardalis with two stars that are much more similar in size and not too dissimilar in luminosity. You can see that the secondary eclipse is quite prominent as well. And the distance between primary eclipses gives you the period. So even though we can't transcribe the orbit like we did before, exactly because observationally these stars are too flat for us to see, we can get the period that we can plug into those equations this way. So it's another neat way to do this. I will talk just really super quickly as a little segue, a sidebar here on Algol, and I'm not going to get too heavy into this. It is actually more complex than just a basic binary. As you can see, there's actually more components to the system that have been found. I won't be talking about that in too much detail, not specifically for Algol, but in more of a general sense. But before I go, I just wanted to mention for those of you that are interested in seeing this star, it's a very interesting star, even though you're not going to be able to resolve the components. It results in a significant brightness change, and you can find it very easily in the spring skies, where Cassiopeia is quite high up. Perseus is not too far behind. Beta Persei is Algol, and it's the second brightest star in the constellation. And the easiest way to do it is to go to Gamma and then just go across about 8 degrees. Gamma and Algol and Alpha Persei actually form a nice little almost isosceles triangle. So that's an easy way to make sure that you're on the right star. Now, Algol, like I said before, you have two stars mutually eclipsing, and it's about a 2.86 day period, just under 3 days. The width of the primary eclipse is about 10 hours. So that's a pretty good chunk of nighttime taken up to watch this whole thing go. Makes it a little tough to see the entire thing. But if you catch the edge of either side of this eclipse, so just near minima, or starting at maxima where it's starting to drop fairly heavily, you can actually see it visually as well as through a simple instrument like a binocular or even a small telescope. This brightness change is very prominent. It's just a little over a magnitude, and it should be visible, especially if you're comparing it in the field of view with other stars in the region that aren't changing brightness. So kind of a fun little project for people. I just thought I'd mention that. Now, the other thing that happens with a lot of these star systems is you might have stars that are just too close to resolve optically, although modern techniques and better optics now have pushed the boundaries of that quite a bit. But typically what we will do is use spectra. We'll use spectra of the two stars in their orbit. And this is called a spectroscopic binary. And it has some ramifications later on that I'll talk about with a couple of more complex star systems. But you can see here, as the stars move, we actually have a change in the spectral lines as they recede and approach us. And of course, when we look at the combined spectra of the stars, especially if they're slightly different spectra, you can actually discern the period that way because these two stars are too close to optically, and they're not tilted in such a way where they'll eclipse. So we can't quite do the same thing that we would do with an eclipsing binary. So basically what happens here is we'll have stars that show up, and depending on the nature of the two, if they're twin stars, we'll have very similar spectra, and then you'll see almost what looks like a splitting of the spectral lines. Then they'll recoalesce and then split again. So in this case, with two similar stars, basically what's happening is we're getting blue shift on one of the components, a red shift on the other one, and then as their relative radial velocity to us it turns to zero, they're non-shifted and almost coalesce. If the two stars are significantly different, we can see the same behavior in other spectral lines that are prominent in each component, and then they can still use this to determine, let's say, from 0 to 0 for the period. And again, using that information, you can then plug that in and discern not only some information about the two stars, but also their orbital angular momentum and so on, and calculate and estimate that. A more extreme situation of this is an example of a sextuple system that is a trio of binaries that are so close that they need to be resolved spectroscopically. And in fact, it's really interesting because there is quite a wide range of stars that are spectroscopic binaries. This one is a particularly more complex example of this, where you have 6 stars or 3 sets of pairs. Very interesting system. To find it, you're basically getting pretty low in the sky. It's in Eridanus, just beside Nu-1 and Nu-2 Eridani. And I don't know if many people would be able to see that very easily with their current equipment, but I just thought for those that are curious about the system, that's where you would find it. I have a better example of one that you can look at more readily. But this leads into multiple system hierarchies, and I'm not going to get into any detail here tonight, but suffice it to say, if we look at a system like this triple system here, you would use on the left-hand side, C is a simplex triple system hierarchy too. So basically what we have here is a pair of stars that are orbiting each other, and then their center of mass is also associated with the primary. There's also in Russia, Tokovinin is an astrophysicist that's studying doubles as well in multiple star systems, and he's come up with a different hierarchical system. So if you happen to be looking in the literature and you see this kind of notation versus this other one, I just thought I'd point it out for edification. But you can see that some of these systems can get very complex. So they're not just strictly twin systems. You can get a whole range of things. The star Castor that's in Gemini, Alpha Geminorum, is actually a sextuple star as well. We see the two bright components, Castor A and B, and they've actually widened a bit. So now they're actually resolvable fairly easily with amateur equipment. But there are other components here. You can see there's quite a few reddish dwarfs here, and we've got the sun here for reference. And you can see here how this whole system is affiliated. And again, using spectroscopy, these are spectroscopic binaries. And then this is a sextuple system as well. And there's quite a few of these sextuple systems around. So using that hierarchy, you can see how Castor is broken out. And I'm not going to get into any detail, but I just thought for those of you that are curious, you can see these orbital periods. And given that, they're in the neighborhood of days or fractions of a day, that means these stars are orbiting each other fairly closely. Okay. For those of you, again, who are new, that want to know where Castor is, basically Betelgeuse on the lower right-hand side here of this diagram is the shoulder of Orion, and Gemini is just above Orion there, and you can find Castor fairly easily. An interesting star to look at. There are other doubles in Gemini as well, but I just thought I'd point out this star. So we're going to leave that alone because, like I said, that's a topic all unto itself, and you could go down a whole rabbit hole with these binaries. I mean, They go from simple to very exotic systems. And this is a good segue into a relatively exotic series of binary stars, novae and supernovae. So one of the things that happens with closer binaries, especially if one of the components has evolved before its partner, is it could become a white dwarf. And it's hot and dense, especially in the early stages before it starts to cool. And it doesn't have a gaseous envelope anymore. It's basically just the shell of what it used to be. Or not shell, sorry, the core of what it used to be, the pit in the cherry, if you will. But its companion might be undergoing its later stages of evolution. And now you might have a red giant. And if these two encounter each other close enough, you can actually get very interesting things happening. So as an example, V Hydrae here is an example of one of these more exotic systems where you have a very dense hot star in a very eccentric orbit, and the companion is a red giant, and every time it comes around about every 8 years in its orbit, it will suck up some material from its partner and superheats it and ejects it out almost like photon torpedoes. And so we will see a brightness difference in the star looking like almost like flares or pulsated flares. And then it goes back out around and then comes back around again. And what's happening basically here is that the material, one of the researchers that was looking at tidal effects, mainly on planetary systems, but it got extended to stellar systems as well, is the French astrophysicist Edouard Roche. And these lobes that are equipotential lobes. So these are areas where you actually have equal gravitational potential in a system where you don't have any major distortion on the top part, what we call detached systems. The materials in these stars don't interact, or these two bodies. As they approach closer, you can get distortion. And so you can imagine like a red dwarf can actually get fairly elongated, especially on an interaction with a dense gravitational field of a partner like a white dwarf or even a neutron star, say, pulling it. And so now that plasma in the outer atmosphere is quite elastic. Obviously, a more extreme case is what Michelle brought up today with the Wolf-Rayet systems. But anyway, when you get a closer approach yet, now these two can actually contact each other and exchange material. A white dwarf doesn't really have any material to exchange because it's basically the core of a very dense core of a star that used to have an envelope and has gone and blown off its layers. But its partner, if it's still evolving, can now drag this out. In extreme case, we get what's called a type 1 supernova. The type 2 supernovae I talked about a couple of talks ago, several months ago, when we were talking about dark nebulae and some of my earlier talks as well. But this mechanism for a type 1 supernovae in an extreme case where you actually get a stellar explosion is exclusive to exotic binary systems. And you can see what happens here. Basically, one of the stars is classified as a white dwarf, and it's very hot and dense. And as it accretes material, it can superheat it. And once you get a nuclear chain reaction, you get a nova and it explodes. So that's kind of pretty funky. I thought you guys would like that one. So that's the kind of thing that happens in these more exotic systems. And we're probably due to have one sometime in the, well, hopefully our lifetime. It would be nice to see one in our galaxy, type 1 supernova, but hopefully we're not too close to it. Anyway, I'll park that part of it. Suffice it to say, there's a lot of different things that go on with these double star systems. And it's very important that we remember these things take all sorts of shapes and sizes, and they're not just simply little cute pairings of stars. Now that leads us into talking about exoplanets. What happens in the case of a stellar system that might have a planetary body associated with it? Well, obviously the complexity of these systems can go up quite dramatically, and orbital dynamics can, especially orbital dynamicists, can have a heyday looking at these types of systems and trying to do all sorts of simulations and calculations. But there's really three possible scenarios for a binary system where you might find a planet around a star system. The first one here is the S-type, where the planet has formed as part of one of the components protoplanetary disks, and it's affiliated closely enough that the two stars won't interact enough to perturb that orbit, so it stays pretty much tight in with the one of the components. That's a fairly stable situation. Whether it leads to the formation of life, again, having a habitable zone is a very complicated question, because depending on the relative orbits of these two stars, it could undergo quite a wide range of illumination and heating, and so it could even dance on the edge of a habitable zone scenario. But suffice it to say, it doesn't mean that a planet can't be in a stable orbit in certain situations. The other extreme is having the planet orbit the mutual barycenter, or the center of mass of the entire system. And if you had two stars that are fairly close together, you could have a planet like even a giant star, or a planet like Jupiter, say, or a super Jupiter, or maybe even a Neptune-sized planet, that could be in a situation where it might get enough illumination from the pair, as long as it's not perturbing the outer planet too far. You could actually get a stable situation where it might actually prelude the formation of life, or at least have a stable orbital scenario. In more extreme cases, if these stars are, this is like with the way this diagram is, you could get serious perturbations that could end up ejecting the planet out of the system altogether, or having it degenerate and crash in, or maybe even spiral into one of the partners like the S-type and transition to maybe a hot Jupiter or something. So it can be very complex, and works progressing on this. The T-type is very interesting, probably likely very rare, but we see this type of behavior with Jupiter and some of the Trojan asteroids that sit in one of the Lagrange points. When you're looking at a three-body problem, there are some stable positions, and these two, L4 and L5, calculated by a French mathematician by the name of Lagrange. These Lagrange points offer some interesting possibilities, because now, as the planet shares the orbit with the low mass star, the relationship between these two stars and the planet stays relatively fixed. So it gets constant illumination. And as long as that is within the habitable zone of that system, that planet could enjoy basically seeing two stars in the sky all the time in the relative similar orientation. But the nice thing is, it's fairly stable, and these 2 points are fairly stable with minimum perturbation. So as long as these two stars don't have too high an eccentricity or mutual orbit, a planet could form around there, and that's a very interesting scenario. So again, work's ongoing, but it's just something to consider when we're looking at some of these stars, and especially as we hear in the news or read literature, Sky and Telescope and some other ones, the factoids about some of these planets. So is there life around multiple star systems? Again, it depends a lot on a lot of factors, but probably the S-type is the most likely candidate, because the T-type, where it's in the Lagrange point, is kind of a very unique scenario. It doesn't mean it won't exist, but less likely to form. So that's the takeaway there. So far, we've just covered just some nuances of some very interesting multiple star systems. We've looked at what causes them to form, how they can be used for understanding stellar dynamics, as well as even exoplanets. And like I said, any of these topics could be easily a talk on their own. So we'll kind of part there and go into how we can look at these things while we have about 20 or 25 minutes left here. So this is something that I particularly like to do. Is I'm a visual observer, and I really enjoy looking at these. Not only are they interesting to view, but some of them are really quite lovely. Striking colors and contrasting colors make them really unique objects to look at. And the nice thing with multiple stars as well, especially when we have a full moon out or not a perfect night as far as sky glow, a lot of these stars can still be looked at with your amateur instrument and be enjoyed, even though you can't dig at the galaxies like what Scott was talking about earlier in his talk. Now, when we're doing observational astronomy on these, there's lists that I'll talk about later that show two parameters: position angle and the separation. And we need both of these in order to characterize that apparent orbit that we were talking about earlier with those diagrams I showed you with 70 Ophiuchi and so on. The position angle will change over time, and so will the separation. Okay, so those are very important things to consider. Alberio Beta Cygni is a well-known double, blue and gold, go Bombers. You can see it even in a small handheld bino. As long as you stabilize it, you can resolve easily those two components, and they're quite lovely, very, very vivid contrasting colors. Now, when we do, if we wanted to measure these, let's say for those of you that want to do some citizen science, say on this, basically the way these are measured, and also for the information when you're referring to these position angles and separations to look up interesting doubles to look at. What we do is we always use north as the sort of main line, and then we measure on an erect image, it would be clockwise, or sorry, counterclockwise around north to get the position angle. And the westward motion, natural motion in the northern hemisphere is 270 degrees always. So the two parameters we're looking at are position angle and separation. And this is a view you'd see in a binocular or a non-inverting telescope where it's erect image. Okay, very important to know. There are some nuances there. If I have a reflector view, we would rotate it 180 degrees, and now east is no longer to the left side. Now it's to the right, and now we're going around. North is down and south is up in this particular case, and so that's very important. The separation hasn't changed, but the position angle measurement has changed, relatively speaking. So this is basically the views in a nutshell. If we were looking due south, erect image view. If we project the north line all the way past, if we were at the meridian here looking due south, it would eventually go to the North Star if we imagine the celestial pole, the celestial sphere, sorry. In the case of an inverting telescope, you will have it rotated 180 degrees, as I already discussed. And then, of course, with a mirror diagonal, which is probably the most common way to view these types of stars with larger instruments, it's just reflected left and right. So it's vertically inverted, but it's, it's vertically inverted, but the orientation up and down is retained. So we just have one flip rather than two. One way to measure these types of stars, for those of you that like to do it, is to use a micro guide type of eyepiece. Both Celestron and Meade made them about 2 decades ago. Yeah, so there is still some new old stock that you can get periodically from some vendors. Most of them now, they've pretty much been discontinued or harder to get now, mainly because a lot of people can do a lot of these measurements with photograph instead of using these reticles. But for those of you that would like to be purists, this is a very interesting eyepiece because you can also do astrometry as well. You can measure relative positions of stars in this case, but you can also do other things like measure the feature on a larger magnified image of Jupiter, say, and be able to estimate its size in kilometers, say, if you wanted to, using a system of eyepieces like this. So you can do some really interesting things, calibrate the focal length of your scope, for example, and so on. But for the purposes of measuring double stars, which is one of the main uses for this, this is taken from the RASC Toronto website. This is a slide where they simulated the view in Stellarium, and in fact, they have a couple of reticles that are very handy. So for those of you that want to kind of get an idea what I'm talking about, you can actually choose those eyepieces and then pick your telescope and see kind of the view you would see. But basically, the tenet here is to utilize this to measure both the position angle, and you need to calibrate the scale in order to get the separation. These are 2 links to 2 different sites that give you some information on how to use these. It's fairly straightforward, but there are some nuances if you're going to get the position angle, again, depending on the telescope type that you're using. So in a nutshell, and I'm just going to briefly cover this, it's not too complicated. What we would do is orient to the west and do a drift of the primary star across the scale, and this would calibrate the scale once we plug in the declination of the star, which is usually well documented. We would do a series of timings and take the average, and then we can now have so many arc seconds per scale division. This is not unlike the plate scale that you would get on a photograph, where you would have so many pixels, arc seconds per pixel, say. And in fact, that's the way you would do it with the photography application, is you would shoot the two stars in the field of view and then measure the pixels. Once it's been calibrated with known separated stars, then you can go ahead and apply it to other systems as well. And then you can use geometry to determine if you do one drift by turning off the mount, you can allow it to drift, and that will give you your west. And then, of course, utilizing that information, you can then do the same thing that you're doing with these visually, but in this case with a photograph. And in some cases, it can be even more accurate. But basically, once we've calibrated the scale, we can get the separation between the two stars by overlaying the scale on them. To get the position angle, you could use this little protractor as an example to get that particular thing. And because we know where west is, because we just drifted, now we can estimate what the position angle is. And again, once we know the orientation that we have for our specific system, optical system, we can actually do those measurements. And you can, this will change depending on where you're aiming the telescope. So like I say, it can get a little complex depending on whether you're pointing north, pointing south, pointing west, and so on. But the orientation of northwest, southeast in an inverting telescope like this, with a star diagonal, as long as the mirror diagonal is parallel to the German, like in a German equatorial mount, the declination axis, this is the relationship that you will see. And of course, you get field rotation as the unit tracks. So I just want to give you a broad overview here. I didn't want to get too heavy into this, but for those of you that are interested, like I said, check those web links out. And this just kind of gives you an idea how you can utilize this to measure the position angle of a double star. A much more easy method, and this is the one I really enjoy, even though I do have that micro guide eyepiece, I also have this one as well. Orion and other companies also have a simple crosshair eyepiece for let's say using for aiming, or you can also use it as a guide eyepiece as well. And it just has a single crosshair and an illuminator that you can dial the brightness to whatever sort of taste you have. And oh my goodness, I didn't mean for this to go. No, sorry about this, guys. Let me just go back up. Oh, you're missing all my goodies here. Apologize. I don't know how that happened. Okay, let me go back here. There we are. All right. Apologies. That was strange. Little hiccup there. Okay, so basically what we do is we do what's called a reticle or cross method. You start out by allowing the, let's say whatever star you have in the middle of the field of view, you center it with the primary centered in the crosshair, and then you let it drift and then adjust the reticle so that it is parallel to the drift, and that's your west motion. And then knowing your system, you can determine whether north is down, up, and so on. That's the only aspect of this that you have to keep in mind, depending on the optical system you have. Once you have that, you recenter the star, and you'll notice here what you want to do now is take the secondary, which is sitting by itself, and you will turn off the mount and time the drift time that it takes to cross the first crosshair vertically there. And that's called B1, B2 in this case. And, this is just an example. If you do a series of timings and you take the average, that'll be your B1, B2 number. Then you you recenter the star after doing that determination, rotate the reticle so it's one of the crosshairs is in line with the system, and you repeat the process, except now you're looking at the drift time till it hits the other crosshair. And that will be your B1, B3. Again, you do a series of timings and take the average. The more careful you are, the better the data you will get. And now you see that you have two equations with two unknowns, because delta is the cosine of the declination of the star. Again, with closer binary pairs, you don't have to worry about the declination differences between the two stars, but it's well cataloged. So now that I have that, I know the timings, I know the cos of the declination, and then all I have is sine theta and s, and now I can determine those two. So you get the separation in arc seconds, and you can get the theta, and the theta is usually within a quadrant, And of course, as long as I know what quadrant I'm in, I would just add 90 degrees or whatever to it, or subtract it from 90 degrees if it's on the other side of this diagram in order to, you just have to use some simple geometry, and away you go. Nice thing with this is it's much easier to do, and it's less cumbersome. There's less room for error as far as interpolating scales and so on. So I really like this method a lot. You just have to know where north and is relative to west in your system in order to make this work. Okay. And it depends on the target you're using, as you saw before with the reticle. But now this will lead into just basically shooting different stars and what they look like in the eyepiece. This is Porrima or Gamma Virginis, and this double star is actually, these are shots taken by Damien Peach. He did one with his, I think he uses a 14-inch for these, February 2003. The separation between the two very similar bright pairs was 0.85 arc seconds, so fairly tiny. Certainly you'd need a larger instrument to resolve those optically. And then in 2005, it was even closer, 0.35. And then here we are, you know, say 13 years later, and now they're 2.5 arc seconds apart. Now, he didn't follow the field rotation to give the apparent orbit like we were talking about before. This is just to show the separation differences over time. But you notice, like we were talking about before on this website here, you can see how these orbits can change depending on the nature of the binary. You know, Zeta Herculi here is, or Hercules is almost 35 years. So in somebody's lifetime, they can follow this orbit all over the place. We're kind of at the point where right now it's widening out quite a bit, but it's starting to you know, certainly within the next 10 or 15 years, we'll start to see it get a little closer to its companion. So this is a nice target to look at as well. Gamma Virginis, you'll see this star system on the apparent orbit, periastron, or the closest approach between the two stars, was right around 2005. Here we are now, 2018 was about where that the abscissa has crossed that curve there, and we're almost into 2025 now. So over the next several decades, it'll actually get wider and wider. So you can see for the scale here, we're going to get into the 3 and 4 arc second regime, and that'll make it much easier to see even with a modest telescope. So where do we find these things? I'm just winding down here fairly quickly. So where do we find these objects in the sky? Well, this is just a smattering. Like, this is a pretty typical southern view in early summer. We have Mu Draconis, Mu Boo, you know, Zeta Boo, Alpha Hercules, 95 Herculi, 70 Ophiuchi. They're all over the place. Okay, but this just sort of shows you that they're not hard to find, and the lists, they're all over the place. So this is kind of a fun thing to do in the summertime, especially, is to just pan around as you're learning the constellations. You'll find quite a few of these, sometimes even by accident. But again, this is just shows you how prevalent some of these more prominent doubles are. If I go into a different region of the sky, proximal to Cygnus, and you know, as it's rising later on in the summer and going or even late spring, you can see Beta Cygni is Albireo that I talked about, the blue and gold earlier. Gamma Delphinus in the constellation Delphinus there. Zeta Cephas, and also Eta Cas, which is also known as Ashard. That's one of my favorites. And we'll talk a little bit about that one in a moment, and a couple of these that I just showed on here. I'm just going to leave this slide up for a minute for those of you that might want to snap a photo of this one. This is a select sample of 101 optical doubles that you can actually see. I should say binary stars or multiple stars that you can find with modest amateur equipment. And they're listed in many lists. This one's taken off the RASC double star lists. You can see that when we look at stars in the eyepiece, they can be everything from twin systems, like what we call matched, to a giant type where you have a slightly different color rendition between the two stars, to ones of unequal mass, where you get a quite a bright star and a very faint companion, to triples, double. For those of you that know in Lyra, you've got not too far away from Vega, there's actually two twin star systems that are slightly different orientation. And again, you can resolve those with modest amateur equipment. Optical binaries are just chance pairings of stars. Usually they're further away, but their parallax is such that at least in modest equipment or smaller aperture scopes, you don't have the resolution to be able to see them move much against the background sky. But from the viewpoint of Earth, they look like a binary system that maybe has a long period. Often some of these will be very pretty to look at anyway, just because they're chance alignment of stars, and they will have significantly different spectra and luminosities. But I just wanted to mention that when you're looking up certain catalogs of multiple stars, some stars haven't been properly cataloged yet, and sometimes the nature of them is uncertain, or they could be a suspected optical star. And I wanted to mention this just because that's what these are. They're not necessarily proven to be fully gravitationally bound systems, and in some cases they won't be at all. Etacast is one of my favorite doubles. The reason I like it is because of the contrasting colors often makes the primary look not necessarily bluish, but it can have an aqua tint to it. The primary can look almost grape-like or a deep mauve color. And there's times that I'll look at it and I go, wow, that's an interesting color. And the next time, even if I look at it 2 or 3 years later, it'll all of a sudden look totally different. It's kind of a chameleon in a way. And as you saw, it's just on the right-hand side of the W of Cassiopeia. Alberio, we've already talked about a lot, but this is the beautiful gold and blue bomber colored star, I guess you could call it. And it's easily available in modest amateur equipment. 95 Hercules is another, or Hercules, I should say, is another one that's slightly blue and gold, but not quite as vivid as Alberio, obviously, and it's a little closer. Mu Draconis is a pair of nearly equally bright stars. And again, you can use these equally bright pairs to test your visual acuity, as well as maybe use to test your optics as well when you're trying to look at the resolving power of your telescope, because you have two very close point sources. That's kind of interesting. Triples, we've got Zeta Cancri, and that's available now into the mid and late spring and into early summer. So that's another one that you might want to look for. It's kind of pretty to look at. Another one that's right now in good position about at this time of night, around 9 or 10 o'clock, is Beta Monocerotis. And you can find it very easily because it forms an isosceles triangle with a line between Betelgeuse and Saiph, which are the left-hand stars of the body of Orion. And, if you complete the triangle here, you can see that the distance from Beta to Betelgeuse is almost the same distance as Betelgeuse to Saiph. Another way to find it is to extend the belt stars over to Gamma and then just hop over about 8 degrees or 10 degrees or so, and you'll find it very easily that way too. And it's quite an interesting star because the position angles are fairly close together, but the separation between the primary and its two secondaries is noticeable, but the two secondary stars are very similar in brightness. So it is quite an interesting star to look at. You don't always need to go super high power, but certainly to resolve them cleanly, it's recommended to go at least 50 to 80 power or more, depending on your experience and ability to look at these. It's kind of a neat star to look at, though. Worthy of study. Of course, Polaris, if you want to check sky conditions, sometimes I'll aim my instrument at Polaris, or for those of you that are using a German equatorial mount, you're going to do a polar alignment anyway. Nice way to determine seeing is if, at modest powers, you can actually see the component Polaris B around Polaris A. And interestingly enough, Polaris A actually has a very close component as well. This is an example of, obviously fringe astrophotography here, but normally it's a spectroscopic binary, but it's sufficiently resolvable under the right conditions. But you have to use specialty photographic equipment to do that, obviously, in this case. For those of you that are more interested in looking at maybe even tighter doubles, here's some examples of some that were done with a 20-inch Ritchie-Chrétien telescope. He used a red and a near infrared filter to look at some of the southern stars. And you can see here we're getting like 1/4 of an arc-second resolution and smaller. Very, very interesting to look at some of these this way. So for those of you that want to challenge, I mean, certainly even if you have an 11 or 14-inch scope, some of these are well within your purview, not necessarily these specific stars, but you can look up lists of stars that I'm going to talk about right away real quickly, and find pairs that might be pairs or triples and multiples that might be a viable option for you to try cutting your teeth through. We're just about done here. I just want to mention here where you can find information on double stars. This particular double star atlas is a very, very nice reference. There's over 2,500 multiples, and the star atlas is really neat because you can actually see the relationship of some of these stars with other deep sky objects. And they do include some of the, like the Messier objects and some of the larger nebulae as well. So if you're doing a little bit of DSO hunting and then want to flip it up and start looking at multiple stars, there's a way to do that. You'll notice that some of these stars have interesting designations on, and those of you who have experience already looking at sky charts, you might see stars listed like this. And I just want to mention that like the Beta, as an example, is S.W. Burnham's catalog, and that's his designation for the star. The unfortunate thing is the Washington Double Star Database, which is basically like an NGC for double stars, an NGC list as an example. We have all of these catalogs from different double star observers that have cataloged both the Struves, the Herschels, Dunlop, Burnham, and so on. And the Washington Double Star Database basically encompasses all of these, but they'll have different designations. So because they can't use Greek symbols, they've used this this standard Roman alphabetic system in order to do this. This is by no means fully comprehensive. It would have taken about 5 slides to cover all of the different designations, but these are the primary ones that you might encounter. And so if you go to do a search, you can also use these like BU and then the star. So like where we had Beta 216 or whatever, or Sigma 60, I would use STF instead. Okay. Now this can also be employed in a really interesting website called Stelladopy. It's an Italian double star site. And the nice thing with this double star site is it actually ties in and regularly interfaces with the Washington Double Star catalog. And these updates are regularly done by the owner, and he does it as a labor of love, I guess you could call it. I would recommend, if you're going to use a site like this, to donate, because it doesn't have annoying pop-up ads like some of the other astronomy sites do. And it's very, very comprehensive and very handy, especially when you're looking at wanting to determine whether a double star might be a viable target. I'll use Gamma Arietis as an example, also known as Mesothelme. This is a double star in Aries with 2 similar components. And you can see at the bottom here, let me see if my mouse will show up. Yes, here it is. This is this caret here will show you the current system that we're looking at. STF 180, meaning sigma 180, if you remember the chart that I gave you here. The AB component, the position angle is 1 degree, separation 7.4, and look at the magnitude difference. It's darn near 0. So these are very similar components here. There's also a third component that's a little further away, 214 arc seconds apart at 81 degrees. And there's a 4 magnitude difference between those. So actually this, what initially looks like a double star, actually has multiple components. And you can see here at the notes, quadruple system, 3 couples separable, 4 stars visible in the system. So for those of you that really want to cut your teeth on some of these, you can really start to dig around and find some real neat gems. If I scroll down the screen here in Stelladopy, I can also see historical data from the Washington Double Star Database. And this shows the current system here, but then you can also look at latest populars. I'll show that in a moment. Nearby doubles. So let's say these are often affiliated with other doubles that are proximal to it. And so if you're looking at one and go, hey, look at this, within an arc minute, within a degree, there's another double star. So I'm just going to check out where that is, and I can hop right over with my, slew it over with my scope. And you might be able to look at a couple of other interesting components as well, targets as well. When you look at populars, these would be the ones that are searched more recently. And of course, it'll be changing all the time. There's over 10,000 records in here. So you could go through all of these and click off, you'll have some common ones here like Aljaba, Castor, Porama, that's Gamma Virginis, Izar and Buddhist, 70 Ophiuchi. So obviously some of the people that have been doing these ones that are in the early parts are the most popular ones, and then they get increasingly less popular. But the nice thing is you have filters as well, limit to visual. So for visual binaries, limit to ones that are telescopic only, known orbit. Maybe you want to do names instead, like you use the star names rather than have the other designators like this. Main double or a physical double, and so on. So it's a very powerful tool to get your feet wet in here. And of course, you can also go in through some of the selections and have binocular doubles, triple systems, whatever. So these neglected lists are ones that haven't been updated in recent past. And of course, for those of you that want to do these double star measurements, once you've gotten really good at it, you can go and select these lists. And maybe if some of the stars are within the range of your instrument, you can then go ahead and add to that. And if you can actually add an observation, then send it to Stella Doppy. There's a site there. I won't get into that tonight, but he'll actually update it. We'll send it to Washington Double Star Database to eventually be included in the list. So that's this section here. One of the nice things with Stella Doppy is you can use it to supplement double star information when you're looking at a star like Arneb in Lepus. You have position angle and separation, but I don't know what the components are. Can I even see this double? It might have a 15th magnitude component, even though it's a second magnitude double star. I don't know. So I kind of need to know that. And unfortunately, with the nature and complexity of systems, there's just probably not enough informational database in Stellarium. It would be too complicated to try and do this, especially when you start getting multiple star systems. So the way we would normally do this is we refer to double Stella Doppy, plug in whatever type of system it is with the name. And then of course, you can see here, this is the information they used here. It's a triple system. There's three components here. One couple is easily separable, and that's the one that they've included in Stellarium. But this other one might potentially be discernible if you magnify it up high enough or use a larger aperture instrument and maybe do a photographic investigation. You could probably capture that other component as well. But this just shows that some of these double star bits of information in Stellarium may only include the easiest of the components to find. So I just wanted to mention that because I thought it was really important that you get an idea. I'm thinking of doing a module during our spring tune-up on Stella Doppy for those of you that are interested in maybe getting your feet wet and really cut your teeth on these double stars. If I've tweaked your interest, we'll be doing an announcement on that shortly, probably within the next couple of days on the main site, and send either myself or James Fast an email. We'll have our email addresses in there. Let me know how many are interested, and so that way we can plan it accordingly. For more information on binary star systems, and this is by no means fully comprehensive, we've already covered Stella Doppy and Dibson Smith already, RASC double stars. There's also a double star certificate that you can get in for the Explore the Universe program as well. So for those of you that want another list of goodies to look for, that's another one that you can do. Sky and Telescope has quite a few nice little articles on some very easy doubles, and these are great to go to the beach and show your friends and family other interesting objects, maybe when planets aren't as easily available or the moon's not available. This is another nice way to kind of impress your neighbors and friends and family of nice objects to look at. And you can pick some of these nice gems as well. For those of you that love Unix sites, NASA has their the Washington Double Star Database available as well. That's the red link down there. And have at or fill your boots. I find Stella Doppy easier because it already accesses the bulk of the information on the WDS anyway. So that in a nutshell is where you can see some of these. So you can see that these doubles and multiple systems are very interesting. There's lots of nuances. They're ongoing, being studied ongoing, and especially with the new tools now that we have at our disposal with interferometric techniques on imaging and so on, and adaptive optics and James Webb Telescope, and now investigations looking at exoplanets. I mean, the list goes on, and I think these are going to be very interesting systems for a long, long time and helped to refine our understanding of not only our galactic inner workings, but also the nature of the universe in general. So thank you very much for your time. I know I went a little bit over and I apologize for that. I hopefully haven't put people to asleep here. If somebody has a couple of questions, I don't know if we have time for maybe one or two, and then maybe I can give you my email address and you can send them to me if you have other ones. I thought I would do this for Jay. In this case, this would be a trinary star system with astrocats. I thought that would be kind of fun to end with that. Any questions, folks? Let me just see if I'll just look at the chat thing here. Somebody posted a bunch of goodies here. Oh, there we are. Okay, yeah, thank you, whoever did that. Cambridge Double Star Atlas, thank you for doing that. I don't know if that was Judy, but thank you for adding those links in there for us. That's great. Yeah, they're about $50 on Amazon for that Cambridge Double Star Atlas. By the way, I forgot to mention, this Double Star Atlas is really nice because in the 4 sections of it, it actually covers some of the hierarchy and additional information on how double stars are cataloged and so on. And then they're broken down by constellation. And of course, there's notes as well in the nature of these star systems, which is really useful information. So it's highly recommended for somebody that's really interested in looking at these. Any questions, anybody? I'll just stop sharing here, unless you need me to refer to my presentation at all for any reason. I guess somebody has fallen asleep. I don't hear anybody. Does anybody have any, like just maybe one question at all? Anyone? I guess not. Well, I thank you for your attention. Looking forward to seeing some of you at our spring tune-up event, and certainly some of you next month when I attend in person. Solar has a double donut. That's pretty funny. I guess you could call it that. Thank you, folks. I appreciate your time tonight. Have a wonderful weekend. Hopefully we don't get inundated with too much of that white stuff, and looking forward to seeing you guys next month to say my fond adieus, because in May I'm going to be pretty much deep into mega packing and finalizing my move. Thanks, everyone. I'll pass it back to Dennis if he's available, or whoever's picking up the microphone at this time. I think